Certo, io sento PDF.
Check, check, 1, 2, check, check. Check, 1, 2. Yeah, and it has a pretty good pickup, so.
Prova. Prova.
Timing myself, so I have.
Yes.
I see the minutes counting down while I.
Okay.
You'll give me one. Yeah, 8 is fine, yeah, yeah. No, eight sounds good. I mean, I'll keep an eye on the time, don't worry. It should be
Okay.
okay. I think I'll be using the mobile microphone, so I can. walk around a
You
little
was
bit.
about to move, okay?
Yeah, yeah, but otherwise I have to sit down and I can't see how.
Okay, we would like to start. If you can have a seat, please. So, welcome again. We start now the session about the astronomy and astrophysics from the moon that aims to show how the moon surface could be a very privileged site for making science and the observation of the universe. So we will start with the first presentation that is by Christian, Brinkering from the Radboud University in Nijmegen. And he will talk about the Astronomical Lunar Observatory, ALO, probing the cosmological dark age and the cosmic dawn with a distributed low-frequency radio array on the lunar far side. Please, welcome. The floor is yours.
Thank you. I hope this microphone works okay. I hope everyone can hear me clearly. So, as I was introduced, my name is Christian Brinkering. I work at the Radboud Radio Lab in the Netherlands. We are connected to the Department of Astrophysics at Radboud University. And we are currently coordinating the efforts of the topical team on radio astronomy from the lunar surface. So we have a particular concept in mind for the kind of facility that we are thinking of, and I hope to introduce you to that today. So without further ado, let's dive right into things. So basically, we are thinking for ALO in terms of many element interferometric array to be deployed on the far side of the moon. And we are thinking of EL3 or the Argonaut lander to be used as a delivery and a platform from which to base the instrument. We are currently consisting of a group, a topical team that's about 70 people all in all, a mix between scientists, engineers, and interested commercial partners. And we have last year also worked on a study where we thought about a precursor instrument to this ALO, because as you will see, ALO is quite an ambitious and complicated project, and we need to get there in a few steps. So this is why we have been thinking in terms of precursor instruments that could go on an earlier launch as well. So what are we primarily focusing on? As I mentioned, we are the radio astronomy topical team, but there's one science case that clearly stands out as the top interesting science case that we want to pursue from the lunar far side. And this is the radio signal from neutral hydrogen in the early universe. So in this diagram above, you see the schematic evolution of the universe with this big blue region before star formation really got underway. So we typically term this the dark ages and the cosmic dawn, when the first stars start shining. And from this age, there's no starlight reaching us, but there is the radio signal from neutral hydrogen, which was, of course, already around. This is heavily redshifted as we observe it today, of course, which means that that 1.4 gigahertz signal is now redshifted into the range below 100 megahertz. So that is currently the biggest open question, is what was happening structure formation-wise in this early universe, and how do we best capture that kind of signal from here? Now, so the motivation for going to the moon is quite clear, right? On Earth, these frequencies below 100 megahertz are heavily polluted with RFI. We have the ionosphere in our way, and so you really need to step out of the Earth's atmosphere, go to a radio quiet place to do research into this signal. So what are our top science goals? As I mentioned, we really want to focus on this, while the interferometric array will be capable of measuring other phenomena at low frequencies as well. We really want to focus and basically design the concept around this science case. And we basically would like to probe the redshift range between Z equals 200 to Z equals 16, which covers all of the dark ages and the cosmic dawn. We would not only like to capture the global signal, the general spectral shape of the signal, as is outlined on the right here. So the red line gives a rough idea of how the signal couples to different physical processes throughout this early universe. Or the universe's history. So the global signal, there are experiments underway also from Earth that are attempting to capture the signal in a certain frequency range. But we also want to measure the spatial power spectrum of the signal, how it varies with the direction we look in and the depth we look at. So the global signal is something that a single well-calibrated antenna should be able to measure. But to measure the power spectrum, you need to be able to distinguish different spatial scales from each other. And also, of course, have sufficient sensitivity to probe into the spectral domain and see what kind of variations you encounter there. So the global signal requires a single antenna, but an extremely well-calibrated one, whereas the power spectrum measurement, the spatial variation of the signal, requires a full interferometric array to be able to distinguish these scales from each other. So what does this look like? Well, basically, an interferometer is sensitive to multiple spatial scales. I see I'm taking way too long for these slides, so I need to speed up. So you measure angles on the sky, you measure structure in frequency space, and that gives you a three-dimensional space, which you can average over in different shells to get different scale sizes for this power spectrum. So the general concept that we are currently looking at is a flat array of 32 by 32 elements, which is the minimum size we expect to yield scientific value for this study. And basically, 32 by 32 antennas means over 1,000 antennas in total, and deploying those from a single lander is extremely challenging if you think about classic antennas in the normal sense. So we need to think in terms of very, very lightweight antennas, unrollable or inflatable structures that are deployed through some kind of hierarchical system from a central point. The antenna size has to be several meters to, couple efficiently to the radiation regime that we're interested in. And they need to be placed close together because that's actually optimal for studying the science case. We want to reach sufficient sensitivity over particular size scales on the sky, and that means the array needs to be compact. So some top-level system requirements. I'll very briefly go through the slide because it's just a few numbers, but we're talking about a rough payload estimate of about 1.5 tons. That's a safe estimate for the capability of EL3. And so the mass per antenna needs to be on the order of 1 kilogram at max for an antenna that's several meters in linear dimension. Power consumption needs to be limited to a few watts per antenna, and so we need to think of ways to locally generate this power per antenna element. And they need to survive, of course, a wide range of temperatures, right? On the lunar fast side, we are blocked from the Earth's RFI, but we are still exposed to sunlight every 2 weeks, half of the time. And that means the temperature range over which our electronics need to survive, being quite exposed as part of these lightweight antennas, is quite wide as well. So there's definitely development needed in this direction. I will skip over the other quantities here. They are derived from the top level requirements. And so how does this array generate its data? Well, we are thinking of using a rectangular, regularly oriented set of antennas in a nicely spaced grid. This means that instead of correlating every antenna with every other antenna, as you would normally do in an interferometer, we can take a spatial FFT per frequency channel and get instant sky images generated this way. And so this gives us snapshots of the sky. And if we understand our instrument well enough, we can interpret those images, do foreground subtraction, account for antenna performance variations, and thus get at the subtle background signal that we want to get the power spectrum of. Of course, accurate modeling of your sky and calibration of your array are extremely important. You really need to know the instrument quite well. So 2 years ago, we did a CDF study with ESA, and basically the result of that is with current technology that's mature enough to start developing in detail, we can do a 4x4 element array, not a 32 by 32 element array. So there's quite a difference between what is currently possible with existing technology and what we would like to have. And that this is why we need to develop technology on several fronts to make this possible. So currently, the focus of our efforts relies on identifying these technology roadmaps and pursuing actual research into them. Another thing about deploying antennas on the lunar surface is that there's quite a few effects that we need to worry about in terms of how radiation interacts with the lunar regolith. So we are looking at low frequency radio waves, and these penetrate into the lunar regolith according to the properties we currently know of the lunar regolith. And that means that we will get reflected signals to some extent. We need to understand how this happens, how bad it gets, what kind of attenuation we get, how these modify the response of the interferometer. And so we really need to talk to experts on lunar regolith structure as well. So that's what I actually hope to do this week as well. So once the interferometer observes this power spectrum, you get all kinds of interesting phenomena that depend on your instrument response. And one of these is that part of your frequency space gets polluted by the strong foregrounds that we have, so the galactic emission and stuff like that. And this is because of the chromatic response of the array. So this is a very important thing that we need to simulate in more detail. And Sonia's talk later today will actually talk about this, about how to better understand the concept of the instrument so we can get ready for these kinds of effects. Because very small errors amount to very large errors that you make in terms of getting your scientific signal of interest out. So basically, the bottom line is that the calibration needs to be accurate to well within 1%, which is way better than you normally need for normal radio observations that we're used to. But once again, Sonia, in her talk, 2 talks after mine, we'll talk about this as well. So the current activities of the topical team are quite broad. We have research going on into various different sub-components of this technology development. So we're talking about the antennas, how to deploy them, what kind of substrate to put them on, how to generate power for all of these antenna elements. Do we do this locally? How do we synchronize the clocks? How do we get the signal out? How do we do that data transmission? Being on the lunar far side means we need infrastructure to bounce our signal back to Earth. So that's an important step as well. So we hope to make use of commercially available communication solutions. And of course, the data processing is another thing that we need to be quite careful about. Anyway, I will stop there because I'm out of time. So thank you very much for your attention. And I hope to be able to chat with you guys later this week as well. Thank you.
Thank you so much, Cristiano. You're perfectly on time. So we go faster to the next speaker, that is Shahab Fatemi of the Department of Physics at Umeå University in Sweden. He will talk about the global hybrid simulation of solar wind interaction with the entire lunar magnetic field.
Good afternoon, everyone. I'm Shahab Fatemi. At the physics department at Umeå University. I'm a plasma physicist and model developer for space plasma. Together with my colleagues, recently we have developed a comprehensive model to study the solar wind interaction with global structures of crustal magnetic fields on the moon with a very high resolution. And well, I don't think I would need to tell you in details, but you know, today moon neither has a global magnetic fields nor has a tenuous exosphere, but instead it has crustal magnetic fields that are heterogeneously spread around the entire lunar surface with various strengths and spatial scales, as you can see from this map here. That is being observed by combination of 2 spacecraft observations of magnetic fields at 30 kilometer altitude above the surface. Here is the lunar far side, and to the sides are the lunar near side. And what is shown here is the strength of crustal fields at 30 kilometer altitude above the surface. The fields are highly non-dipolar and with various strengths. So it's extremely important that when it comes to the solar wind interaction with crustal fields, it creates a very fundamental and fundamental plasma physics, because the interaction in general occurs at sub-ion inertial length scales due to the small scale of the crustal magnetic fields compared to the characteristic length scales of plasma. For example, the ion gyro radius is extremely large compared to the spatial scales of these crustal fields. Nevertheless, the strength of fields are large enough that can create surface shielding, and even a shock formation has been observed recently. Here on this picture, this is quite old, almost 10, 12 years old, from Chandrayaan observation. It shows the flux of solar wind photons that are coming off from the lunar surface. And that's the background color. And the lines show the strength of the crustal fields. You can see there is a correlation between the highest strength of crustal fields, this is the lunar far side, and the plasma, that is the solar wind photons that are coming off from the lunar surface. So in general, the take-home message here is that the interaction is kinetic because there's a lot of kinetic processes going on, and then the kinetic processes play a crucial role. Therefore, the moon and studying the crustal field is not an MHD model. So previous kinetic simulations have focused on localized magnetic fields. For example, a series by Deca et al. And Bamford et al. They have looked at either on a single dipole interaction or with a very localized magnetic fields on the surface of the moon. We have developed AMIRIS. AMIRIS is the framework. It's a three-dimensional time-dependent hybrid model of plasma. By hybrid, I mean that's a kinetic ions and electrons are fluid, charge neutralizer fluid. I'm the developer of the code. It's a heavily parallelized code that runs on multiple graphic processing units, GPUs for computation that allows us to run the code with a very high with energy efficient as well as very high resolution. We have combined it with a spherical harmonic model of lunar crustal magnetic field, the recent one by Rabat et al. There is a technical issue in here because when we want to study the solar wind interaction with the surface, the spherical harmonics are usually underestimating the strength of the fields. Therefore, we needed to amplify the strength of the fields by a factor of 2. We have used a typical solar wind condition near the moon for various lunar phases. We have been tested for different phases of the moon as it has been moving around the Earth during the time that is in the solar wind from the waning to the waxing time periods. And the simulation sense sizes are 15 kilometers. That's half a degree on the surface of the moon for a global scale. This is an example of the crustal fields that are included into our simulation here. And as an example here, I've marked up the Rainer gamma. And Rainer gamma during this phase that we have been looking at, that's corresponding to day 25 in this picture to the left. Rainer gamma was almost located at the terminator because that's the region of our interest to look at the localized interaction with Rainer gamma with lunar vertex mission that I come talk about it in a minute. Here I show a classical Vega structure using our model. This is during the condition that the crustal fields are not included into the model. In the bottom, we see the plasma density, and on the top, it shows the magnitude of the magnetic field. This is a classical structure. There is nothing happening in the upstream. Solar wind is coming from the right to the left. And here we do see a cavity, as well as we do see a magnetic field enhancement that has been observed by several spacecrafts during 60s and 70s. When we include the crustal field, however, you can see that there are a lot of disturbances happening both upstream of the moon as well as in the wake. Here we have made the color bar, the limit of our color bar such that it matches with the condition that there is no crustal field, so don't get confused by these extremely large pattern here. Those are nearly around 10, 15 nanotesla at 100 kilometers that has been sometimes observed by different spacecraft. Here we can also see a limb compression that is a plasma density enhancement that has been on and off or intermittently observed during the different lunar phases, and that is associated with the IMF orientation as well as the solar wind condition. A little bit into the detail of the structure here, what we are seeing is that we are looking at the lunar surface viewed from the sun. And in this row here, in this column here, we do see the condition that the crustal fields are not included. On top is the magnetic field. So there is no disturbance to the magnetic field, as well as no disturbances in the downgoing solar wind flux, other than the cosine solar zenith angle dependence. This is the electric field that is pointing up, and there is no reflection from the lunar surface, because when the solar wind is coming to the surface, everything impacting to the surface gets absorbed and removed. Here is for 3 different conditions that then we have included the lunar crustal fields. On top, you can see it for different lunar phases. As a tracer, I have marked the Grazimovich, and then you can see that different lunar phases, the location of Grazimovich has shifted. And you can see there are considerable perturbations and effects on the downgoing solar wind flux, especially during the condition that, for example, the South Pole Basin is located at terminator. Here on this row, we show the electric field, the contribution of electric field on both decelerating and accelerating plasma that is partially shielding, for example, the lunar surface from the incident of the solar wind. For example, we can see it very clearly here, as well as the plasma reflection. The total or the percentage of the solar wind reflection from our model is nearly 10–20%. That is also consistent with previous observations by both Chandrayaan and Artemis. We can use our model to study a very localized interaction with crustal fields as well. This is zoomed in into the Rainer gamma that I showed you before. And we can see, and we have looked at how much for a specific lunar phase, I should mention that is here, and then for a specific solar wind condition, we do see that there is a shadow for the solar wind photon density because the solar wind is coming from the left to the right in this picture, and the Rainer gamma over the southern region has been capable of reducing the plasma density that is impacting the surface as well as the flux. There is also a flux reduction at different regions. So this is the why we have focused on Rainer gamma is because with Lunar Vertex, that's the future mission, we are going to land and operate in April 2024 on Rainer gamma, and we are going to traverse with a lander with a rover for nearly half a kilometer in Rainer gamma region, try to understand the pattern of the swirls as well as the crustal magnetic fields. But it's extremely important for us to know how much plasma is coming down to the surface at any specific region. So if you're interested to know about the mission, I encourage you to see the poster tomorrow by David Blewett. Unfortunately, he couldn't come, but I will present it. And I would be happy to take questions if there are any in the QA session. Thank you.
Thank you so much. Okay, so we have the next speaker. That is Sonia Ghosh. So coming back to the HALO study. And she will talk about the effect of the antenna position offsets on the redshift 21 centimeter signal power spectrum of the Astrophysical Lunar Observatory HALO study. The floor is yours. Thank you.
So good afternoon, everyone. My name is Sonia Ghosh, and I'm a first-year PhD student at the Kaptan Astronomical Institute affiliated with the University of Groningen. I primarily work with Professor Leon Koopmans in collaboration with Dr. Christian Brinkering, who is here with us today, Dr. Mark Leinvold, and Dr. Albert-Jan Boonstra. So building upon the introduction that Christian gave us about the HALO concept, now I will be going to talk about my study with HALO, in particular the effects of antenna position offset on the 21 centimeter power spectrum. And please remember that this is an ongoing work, and the final goal is to establish a framework where we can study the various systematics that might affect the performance of HALO. Now, before I begin, I would like to express my gratitude to the organizers for conducting this beautiful conference and giving me this opportunity to present my research. So we already, okay. Yeah, so we already heard that HALO, which stands for Astrophysical Lunar Observatory, is a science payload for the EL3 mission. And it is envisioned that it will be a low frequency radio interferometric array operating on the lunar far side. So the science driver behind such an infrastructure is basically the 21 centimeter line from the hydrogen that is coming from the most pristine period of the universe evolution called the Dark Ages, and the subsequent period called the Cosmic Dawn. Now, since it is expected that the signal of interest is going to peak at around 30 megahertz and at 70 megahertz for the periods of Dark Ages and Cosmic Dawn respectively, so HALO is planned to operate on a large bandwidth, approximately spanning from 7 to 70 megahertz. And here I show you an artist's depiction of the full-scale HALO on the lunar surface. Now, moving into my project. So since HALO is expected to work as an FFT telescope, it is essential for the antennas to be placed on a regular grid. And any non-redundancy that might be introduced by the antenna position offset or by beam-to-beam variation will lead to uncertainty in the power spectrum measurements, and it will contaminate the EOR window. And that is where my work comes into picture. So we know in realistic scenario that the deployment of the dipoles on the lunar surface might be flawed, and that might introduce errors in the antenna positions and orientation with respect to the planned position. And these errors then might get propagated to the data processing chain, and hence it will impact the extraction of the 21 centimeter signal. For my current analysis, I am focusing only on the antenna position offset and trying to understand how it impacts the 2D power spectrum. And here we need to remember that the final goal is to be able to define the acceptable tolerance level for our given sensitivity goals and how they propagate into the images. Now, for this, intuitively, it is helpful for us to have a simulation where we can put the non-idealities that we know will be there along with the array layout, and then try to analyze the how it affects the recovery of the signal. And so for this, it is very essential to have an end-to-end forward simulation pipeline, and that is what I'm trying to do here. So what I show here is the schematic diagram of the first order framework of the forward simulation pipeline that I'm trying to develop. And in its current iteration, it takes into account the input array layout, which might be regular or an irregular array. By irregular, I mean I'm introducing the antenna position offset, drawing the random error from a zero mean Gaussian distribution with a parameterized standard deviation. Now, the idea is to vary the value of the standard deviation so that we can investigate on the various varying levels of the perturbed antenna position. Now, once we have the array layout, we generate mock interferometric observation using this software called Oscar. And upon having the mock data, we introduce a sky model. Now, for the sky model, we start off with a diffused galactic radiation. And in the radio interferometry jargon, we call this the galactic foreground. And so once we have the sky map, we can extrapolate it to our frequency with the help of the global sky model. And then what we try to do is to understand how this might impact the, because we need to remember that the signal that we are trying to detect is hidden beneath this foreground. And the large part of the actual signal that we receive is contributed by this foreground. So it is very essential to effectively model the foreground and try to understand its impact on the power spectrum estimation. Right. So once we have the sky model and the array layout, we try to simulate the visibilities and try to see what kind of images we might get for ALO. Here you see the point split function or the synthesized beam. Now, you can imagine this to be what the interferometer sees when a point source is directly overhead the array. So you can assume it to be the eye of the interferometer. Now, for the lower frequency, you see that we have a central main lobe with some side lobes. But as we increase the frequency and go to the higher frequency, we see increasing number of grating lobes, right? And why is that? Now, the grating lobe itself is a consequence of the regular array that we are planning to have. And and as we increase the frequency, the electric field is highly undersampled. That leads to the increase in the number of the grating lobes. And the consequence is that when we get the final image of the sky from ALO-like array, we see something like this. So at lower frequency, you clearly see that we have a proper sky image that we expect to get. But as we go to the higher frequency, we get the same image of the sky in a repetitive form shifted around. So you can clearly see the impact of the PSF. And so we have to be very mindful while designing the size of the antenna while building up ALO, and also try to develop a clever technique to get rid of these imaging artifacts. Then finally, we generate a cylindrically averaged power spectrum with a pipeline called PSPipe. And here you see the 2D power spectrum for a regular array layout that ALO will see. And if you remember, Christian has already showed in his talk that you may find the resemblance of a foreground wedge here. And the blue region here is the region where we actually want to have high sensitivity in order to detect the 21 centimeter signal. So the takeaway message from this slide is that this results validates the expected result that we want to have and also provide us like a sanity check if the simulation pipeline is actually giving us the correct result or not. And this is my last slide. So to conclude with, my talk is focused on the antenna position offset does have a potential impact on the power spectrum estimation. And as a first order investigation, we are trying to understand the positional offsets, the impact on the power point spread function, the 2D power spectrum. And the final goal is to develop a framework where we can give an acceptable tolerance level for the dipole placement errors. And for the future work, I want to include the beam model, the 21 centimeter model itself in order to make the simulation more realistic and hence give the acceptable tolerance level. And with this, I'll conclude my slide.
Thank you so much, Ray, for this very interesting report. And we can go to the next speaker, that is Chris Van Dijk from the Cosin Remote Sensing Company. He will talk about pale polarized dots, spectropolarimetry of the Earth as an exoplanet with the loop. Thank you.
Hello. Yeah. Okay. So my name is Chris. I work at the Dutch company Cosine. And I'm here to talk to you today about a fun new payload that we've been working on called Loop. Clicky thing. Great. Just to skip through the formalities very quickly. This is a collaboration of 2 Dutch universities and ourselves at Cosine. TU Delft are working on the science case and science requirements, of course. Leiden University are working on the measurement principle and the preliminary optical design, and us as Cosine, we do the systems design and the hardware realization. Most of what I'm talking about today has been presented in a paper that you can find more information about than the 10-minute lightning talk I'm about to give. Now, on to the fun stuff. So, what is Loop and why do we want Loop? It's developed within the context of searching for life on exoplanets. Now, a very promising technique for finding life on exoplanets is to use spectropolarimetry. If you have, this is actually direct imaging via spectropolarimetry. If you have a look at some simulated spectra here for an Earth-like planet that has the typical features that you would expect, so forests, ocean, clouds, you can see all our familiar signals here, the green bumps and the red edge from vegetation. We see some nice contrast here from liquid oceans. If we have a look not just at the spectral and polarization flux components, but also the degree of polarization as a function of the, let's say, the Earth-Sun phase angle. Here, you can see the familiar features of, for example, the rainbow. If there was ice crystals here, you would also see a corresponding cloud bow from Mie scattering. We also see here familiar bump from Rayleigh scattering through the atmosphere. So this is shaping up to be a very promising technique for being able to look for the typical signs that you would need for life on exoplanets. So the point of Loop is to use the Earth as a model system for developing then the next generation of observatories to then go forward and look for these signs on exoplanets. And the moon is a very excellent vantage point for being able to do these measurements. It's far enough away that we're not concerned too much about the angular dependence of, for example, polarimetry satellites in LEO. We are able to do all of the phase angles of both the daily rotation of the Earth and the phase angle function of the Earth-Sun system. So that's something that we don't really get from, for example, the Earthshine data. And so what we're really hoping to do here is to design a payload that is able to retrieve the spectral flux, the angle, and the degree of polarization as a function of the phase angle of the system. So that's the first two Stokes parameters plus spectrum. This is it. It's actually an extremely compact optical payload. It's essentially a monolithic optical slab. You can see here that it's composed of a number of optical elements here in a stack on top of a familiar detector that I'll explain in a moment. What we have is a Fabry-Pro Epsilon for doing the spectral filtering. We have a patterned liquid crystal retarder. So this is acting as our polarization modulation. We are using a detector that's quite familiar to us at Cosine. It's a 12 megapixel V-near FPA. What we actually put on top here is a micro lens array. So this gives us actually the ability to develop a snapshot imaging where in a single frame, we're actually able to collect both the spectral and polarization data that we need. The micro lens array itself is 150 by 75 lenslets. So this is a very large number of lenslets. This gives us a high degree of redundancy, which is actually quite useful if you're doing something like operating on the lunar surface with regolith. And then in a single frame, we're actually able to capture quite a dense data set. I can show you here what a single frame looks like. I'll try and break it down and walk through it a little bit. What we have here on the vertical axis is a linearly varying filter. This is the Fabry-Pro that I mentioned. So in the vertical direction, the center wavelength is continuously varying from 400 to 1000 nanometers. Along the horizontal axis, we have the modulation direction of our polarizer. So then we have the polarization signal in this axis, and then the 2D product of these two separate filters then gives us our complete spectropolarimetric data set. The micro lens array on top gives us a large number of dots on the sensor. These are then the individual observations of the Earth. The position of the dot relative to the lenslet will give us information about the angle of incidence relative to the lens array. This is actually quite useful for doing the reconstruction of the polarization signal and the effect of the optics based on the ray tracing going through the system. And by deconstructing this large data set, then we're actually able to generate a nice data set here, where you can see that we have the first two Stokes parameters as a function of wavelength. You can see this here on the vertical axis. And you're able to, and this is actually a simulated image for a polarized Earth-like planet. You can see here familiar features like the water band in the near, the A band of oxygen here in the green. And if you look carefully in the Rayleigh area, you can see modulation in the polarization signal. So this has been how we can actually get back the large degree of polarization as a function of phase angle through multiple measurements. In terms of the system design, this is actually based off of a system that at Cosine we've flown a number of times by now. This is our Hyperscout imager, pictured on the right here. What we've taken is the core of Hyperscout, which is our focal plane array. It's an FPGA-based acquisition board, which we've already flown a number of times. It's actually quite proven technology. It's also quite compact. The focal plane array itself is, let's say, credit card size, 60 by 40 millimeters. And the back-end electronics is the familiar 1U CubeSat form factor of 90 by 90 millimeters. And this is actually also, this is a little advertising plug here, about to fly on ESA's Hera mission for the planetary defense. We're actually flying one of these Hyperscouts on board there as well. So at a glance, what we want is to have daily imaging of the Earth so that we can get the Earth rotation and also the phase angles over the course of the evolution of the system. Hourly observations give us enough information about the rotation of the Earth. In terms of ConOps, this is actually quite low impact. We're looking at something like 1 kilojoule 2 megabytes will give us a minimum viable data product, giving us something around about 50 megabytes per day downlink. The field of view of the instrument is actually quite wide. If you remember, the Earth's about 2 degrees in the sky, but with a 20 by 20 degree field of view, we don't need a very accurate pointing in order to be able to collect the data product. That's useful for like a low barrier addition to as a secondary payload. As I mentioned, the spectral range is from 400 to 1000 nanometers, with a resolution of around about 15 nanometers. And we're using a 12-bit CMOS detector, which gives us a polarimetric sensitivity of order of about 10 to the minus 3. So, right on time. What I've shown is a very simple, compact payload that can deliver both the spectral flux and the first 2 Stokes parameters of polarization as a function of phase angle. The point here is to observe the Earth as an exoplanet within the context of searching for signs of life on exoplanets for future observatories. And right now, we're already at the point of trying to see if we can find some IOD opportunities. So if anyone knows of any, please get in contact with us, CoSign, or any of the members of the team. Thank you.
1 minute before. Wow. Thank you so much. Yes. So we can go to the last talk of this session. Professor Bernard Cohen, leader Amsterdam University and CEO of the European Mars Earth Space Innovation. So the talk is about astronomy and space science from moon, past experiments, and current prospects.
Yeah, thank you very much.
Thank you
So
so
it's
much.
a pleasure to be here in this session. And back to my youth, where I started as an astronomer, and then I became a lunar mission scientist. I'm going to tell you a bit this little story. But astronomy from the moon is an area where we have done some studies, but also now we are preparing the next phase. So at the same time, I'm going to advertise some of the work of my collaborators that will be presented in different sessions, which is linked also not only with science from the moon, astronomy, but also science of the moon or science on the moon, life science. And this is illustrated by some of this slide where you see what we have deployed in a program called Your Moon Mars. So it was before Earth Moon Mars, where we developed a program to analyze data, to develop instruments, to test them in the field, to go in some habitat, and then do some simulation of what we'll have in the moon base. And we'll see at the end that this has also a link with astronomy and space science you could do from a moon base. So as I mentioned, I started as an astronomer. So I was at European Southern Observatory. When I came back to Europe, I worked at ESA. And so I was doing astronomy. But I organized my first conference on astronomy and space science on the moon was like 30 years ago at COSPA in Washington. And okay, we were describing what we could do, put telescopes, radio telescope, infrared, solar, planetary observations. And then we created this International Lunar Exploration Working Group with all science represented, the industry and so on. But because I organized this session on science from the moon, I was labeled a lunar scientist. So right after that, we did also some work on how to protect the lunar environment. And then they were looking for somebody to run the first mission to the moon. So they picked me, and I was then in charge of Smart One, our first ESA mission to the moon. You can see it there. And then this was launched 20 years ago, and we were then alone around the moon at the time. But now we have a beautiful orbital village, a fleet all around the moon. We had Kaguya, we had Chang'e 1, then Chang'e 2, and then we had Chandrayaan 1, where actually I was negotiating to put 3 ESA payload on board, as it was mentioned this morning. So indeed, 20 years ago, ESA had a mission at the moon, the first of this millennium. It took us 3 years to build this mission. And then now we had to wait 20 years not to build a mission. So I don't know, something we have to see how we can learn to work a bit faster. But now we have some nice payload which are prepared for future mission. But this is a mission where for 100 million euro, we went to the moon and we brought some instruments, and also we deployed an ion engine. So from the science of the moon, we did some remote sensing, studying tectonics, cratering, volcanism. Even we surveyed the polar region for the first time, and we even did our own impact, which was observed from Canada, France, Hawaii telescope in 2006. So eventually, we also made a survey of the south polar region of the moon. So this is actually a mosaic that was produced with our camera. You see very interesting area there, which we can use for future exploration, for science, also for emplacing bays, for emplacing telescopes as well. Eventually, we also found, close to the south pole of the moon, a ridge, we call it the Smart 1 peak of light, where you have the maximum amount of light even in winter, and which is now one of the sites that is planned for Artemis future mission. So what about signal from the moon then? You saw this impact flash of Smart 1. At the same time, we were monitoring from an array of radio observatories from Earth one song of Smart 1 because we had no fuel left, so we had to do a touchdown. And so you can see some nice, from Italy, two sites observed, from Australia, and also from Brazil. And eventually, this is the last signals that we received from the Smart 1 spacecraft. At the time when the signal died, we got in real time this picture of the impact from Canada, France, Hawaii. So it was quite interesting, multi-wavelength observation. So what we did 25 years ago, we created an international lunar exploration working group to coordinate what the different agencies and stakeholders would do with a step-by-step precursor orbital mission, robotic village, outpost, and moon base. So what could we do then in the area of astronomy with this roadmap? So as you know, no atmosphere, all wavelengths are accessible, good seismic stability, avoid dust, that's what we have to take care, but a great place to monitor the Earth, the sun, the planets. We even had an interesting idea. You just put a telescope and just let it fix. And then the sky can just gently drift and you could monitor variability. Even you could monitor weak lensing and do a bit what we do with Euclid, but okay, Euclid is better. Do variability studies, deep sky telescope. You can deploy a liquid mirror telescope of 30 meters that will be 10 times deeper than James Webb Space Telescope. Also, you have the coldest areas in the solar system, 40 Kelvin in the permanent shadow region, great for far infrared. And also, you can measure high energy radiation or even particles, X-ray, gamma rays. But you can also use the soil as a Cherenkov detector. And like we use the atmosphere as a Cherenkov detector, but there you could detect particles of 10 to the 20 electron volt. Here's an example of a paper we published about lunar liquid mirror telescope at the moon with Roger Angel and Bora and Pete Warden. And we just had the data from Smart 1 at the time from the North Pole. So we found the best place where to position it. We developed at the time of Google Lunar X Prize, a small lander, and then we put a telescope on it, and then we tested to teleoperate it from a moon base that we built at ESTEC. And eventually we put it in another country and we teleoperated this telescope as it would be on the moon. And you can see when you will have the telescope on the moon, this is what we obtained with this telescope. You could observe the Earth. The Earth is 4 times bigger and 60 times brighter than the moon, the full moon. But we did this test using a telescope to monitor the moon, but it to be the Earth, but also to monitor the sun, to monitor planet, and also to use, you can use a telescope to monitor a scene where you send a robot, an astronaut, 2 or 5 kilometers distant. You can then spy on the astronauts from Earth. So we organize also a workshop where we put all these people using telescope and instruments. As you know, we have started a robotic village on the moon. 2013, Chang'e 3 landed, deployed a rover, which was short-lived, but then had a telescope, a 20-centimeter telescope in UV that is still in operation after 10 years. So we have a telescope on the moon. Now, what about radio astronomy? We've heard about this beautiful radio telescope and so on. We don't have the Earth ionosphere on the moon, a bit of daylight ionosphere. You have also to take into account the fact that because of interstellar scattering, you don't have an absolute angular resolution, so you have a scaling law here. So if you have 1 megahertz, you have a 22 arc-minute Ponce function. So it's not very good images, but if you go a bit bigger in the 20 megahertz, you can still make some nice maps. You have also a time of spreading in time of the signal due also to interstellar medium. And okay, we have heard about the fact that as a function of redshift, this is the signal that you have from for different redshift, and then everything is piling up if you look back in the past. So in this low frequency area, in particular this 21 centimeter band. So we tried to do a demo with some radio telescope. Here we looked at very close sites, looking at the sun, looking at Jupiter, in particular this Jupiter radio burst, eventually a bit of the Milky Way. And we monitored it. So this is the solar spectrum, you know, radio bursts with the different time variations. And you could try to, monitor the giant planet. Here is an image you could obtain. This was obtained by a probe, which was at Jupiter, a beautiful image, but you could do that with an interferometer from Earth. And we monitor also the IO. And eventually, you can also monitor some galactic sources also with some of these precursors. So for this, we deployed, you have some factors to take into account, reflection of the regolith and so on, we discussed that. But we deployed a precursor experiment in collaboration with the DLR, Robotic Mechatronics Institute. Okay, we went at Etna, very similar soil. And then we deployed a number of instruments there, in particular an interferometric array of 4 radio telescopes that we deployed last June in 2022, also as a demonstration of what you could do on the moon. We also did some work deploying some instruments using some astronauts. And of course, that would be in preparation for the future, where we'll have also humans that could deploy some of these telescopes. Now, there are many challenges for that. I would just end in advertising some of the posters which are presented. So we are looking some astronauts for 1 week in a moon base. So we are looking for volunteers to look at the poster. One of also our collaborators, Serena, has built a portable moon base, and maybe we are going to bring it on Thursday and Friday evening here. That's a place you can borrow it for 1 month. That's how it looks like. And this is to train researcher. And so you will see possibly it on Friday. And eventually we have also, I'm directing a base on Hawaii, where we are also organizing a field expedition where you can test some of your instruments and your science. So this is with Hank Rogers, Mr. Tetris. And we have recovered. So we have a nice mission control center in Hawaii. And that's how the base looks like. So I want to invite you to come test your instruments, your telescope, your EVA protocol. We have done that for 2 years. We recovered from COVID and from the giant eruption. So we went there again in March. And so now all these field activities, we try to put them, use them for credit on the worldwide Eurospace Hub or Earth Moon Mars Academy, where you can go some training. And so we have now obtained a funding from the European Commission to fund researchers, astronaut field campaign. So if you're interested to join, please come see some of the posters and those presentations. And so beyond astronomy from the moon, also we realized that training astronauts to use some of these bias instruments will be also very synergetic, and we will help also to feed forward the design of real mission that we are going to send. Thank you very much for your patience.
Really, thank you so much for this very comprehensive work and showing us that the moon is a very revolution now for science. So we have in front of us the opportunity to expand our knowledge of the universe, of the Earth, of the solar system, thanks to the fact that we are going now to the moon. Thank you so much. Please, if you want, you can stay here because we start now the question and answer part, and I invite also the other speaker, please, that can come here. So if, okay, there is the other microphone working now, okay? So you can reply with this one, so. Okay. Any question? Yeah, please there. Just a minute, because otherwise online they cannot hear or you.
Hello. Hello. Okay. I have a question about the hybrid modeling. I really enjoyed the presentation. I was wondering if you had looked at or were planning to look at how these structures respond when the moon moves through Earth's magnetotail.
Well, in the tail, the density and dynamic pressure are not that high, so they would not affect the crustal fields, I believe. We have not looked at it, but since the pressure is not that much, then the structure of crustal fields would stay as that has been included in the model. We have looked at it in the magnetosheath. In the magnetosheath, due to the high dynamic pressure of the plasma in the sheath, majority of the crustal fields are compressed down to the surface, but we have not looked at the tail, no.
Thank you.
I have two questions. One is for the blue dot person, and my question is, with this 20 by 20 degree field of view, will there ever be something else that's bright enough beyond Earth, like a bright planet or whatever, or like real bright star that you could actually observe with that thing?
Well, the first and most obvious one is the sun. That limits the phase angles that we're able to observe to the larger angles. As soon as we get too close to the Earth, and we're not able to differentiate between the direct light from the sun and the light through the Earth. The other one that we were concerned about was if, for example, we're landed near the poles, then the Earth tends to be quite low in the sky. So we may also get some stray light from the lunar surface itself. Those were the main two contributions that we're looking at, baffling strategies in order to sort of increase the observational period of those two contributions. But in terms of other solar objects, we haven't considered this yet. I think the intensities are quite different between the light from the Earth and the next brightest object, which is probably Venus or something.
Okay, thanks. And I have a question for the radio telescope, these ALU people. So have you considered a non-regular grid? Of course, you can't do the simplest FFT because non-regular grid will help you with all these grating artifacts. And of course, you can't use the simplest FFT imaging, but you can kind of, just, double the FFT grid and just occupy half the cells, so some version like that as a compromise between fully randomized grid or fully regular grid.
So that's a very valid point, and that's exactly what Sonia is working on. So I thought she would pick up the answer there. But that's very valid. So the primary concern with us trying to put this in a regular grid is, of course, the data rate that comes out, right? And the processing required to treat all the antennas. So you can't do individual correlations. But a midway might be achievable, right? Where you have multiple subgrids, maybe offset in interesting ways to basically limit the effect of these grating lobes. You can't get rid of them altogether because there's some degree of regularity involved for processing power's sake. which does mean that you will always get grating lobes at the higher frequencies. There's no way to completely avoid that effect, I'm afraid. But indeed, yeah, several subgrids working together might alleviate it well enough to circumvent the fundamental problem. But of course, detailed simulations will have to help us with this to get a very clear idea about how bad these effects get and how well we can mitigate them.
Thank you.
Other question? Okay, I have a question for Werner. Just a curiosity, you spoke about this liquid mirror telescope. How do you think this can advance the performances with respect to James Webb? What about the cost, the feasibility of realizing something like this on the moon?
Yeah, so there are some existing liquid mirror telescopes, and they were developed in Canada, Barbara, and also in the US. So they could reach 3-4 meters. And so we were looking at the 30-meter class, and actually that's pointing always in the same direction first. So it's really a telescope like a pencil into the past. And just because of a bit of the libration of the moon, you can map an area around, but you would have access to a 30-meter, mostly dish collector, well, light collector, not very high precision in terms of images, but really big collector. And so, we looked at some material that could be working. So we had some small demonstration, okay, we thought at something that could be next generation after James Webb, or maybe even they could be used in other wavelengths as well. And so they could also be complementary to what we would do with LUVOIR or other very gigantic mirror on Earth, but in wavelength range which are not accessible from Earth.
Yeah, thank you. Thank you so much. Any other question? Okay, if there are no other questions, I would thank so much all the speakers of the session. Thank you so much, everybody.
So I just have a question for the audience. If some of you are looking for a grant, a research grant, or a grant to use our field site, or a grant to have your own startup, please contact us, because we have now a scheme where we have startup money to fund researchers. Thank you.
Okay, so I leave the ball to the next session and the next chair. That is, okay, okay, who is the next? The Moon as an observation and communication platform. So Sonia Ghosh, which chair?
Hello, everyone. Again, my name is Sonia Ghosh. We just met a few moments back. So I will be chairing this session. Our first speaker is Jan Harms, who is going to speak about the lunar gravitational wave antenna. And once you're ready, the floor is yours.
Thank you very much. Okay, so lunar gravitational wave antenna. The first question might be, after the 4, soon 5 terrestrial detectors that we have, asking money for yet another 2 in the future, and these are being approved, if we need yet another gravitational wave detector. And good question. So the scenario is quite similar to what we know from the EM world. Over the next decade, 1 to decades, we will have a wide band of observation frequencies from the very low frequencies observed with the B-mode polarizations up to a few kilohertz with the terrestrial detectors. And now, of course, we are not continuously covering that band. There are some gaps, but you know, one of these gaps is scientifically quite important as far as we know, and that's the decihertz band between LISA and the terrestrial detectors. And that situation is called the missing link. We have no very great idea so far what detector we could build to observe gravitational waves in the decihertz band. And that's where the moon plays a role. So what we propose is essentially the following. Well, that didn't work. I will try this again. I think that's not going to work. No, I have to somehow skip that slide. Okay. Anyway, that slide was supposed to show to you. Well, I'm not sure what's happening here. Okay. Let me then try to skip it. So I skipped that slide, explain to you. So the moon essentially acts as a receiver for space-time fluctuations. That means gravitational waves passing the moon induce quadrupolar vibrations of the moon. And the response of the moon is actually quite complex. So here are resonance frequencies of many quadrupolar modes of the moon. And we can simulate this in so-called null-mode simulations. Now, these are quite reliable, you know, at millihertz and a few tenths of millihertz, but in the very important decihertz band, they are not reliable. For example, the features that we currently see in these null-mode simulations, they do not reproduce at all the observations that we have from Apollo of meteoroid impacts, for example, which showed that the ground has very high Q values actually, and have very long observation times for individual events. So that tells us that the actual response of the decihertz band is much larger than what we currently see in these normal mode simulations. So we need finite element simulations that take topography and geology into account as much as we can and know, and then rerun these analyses. Now, what we propose is the deployment of 4 seismic stations on the moon in a, of order kilometer diameter array. Now we need the array because we want to be able to distinguish in a better way between the seismic background that comes from moonquakes and meteoroid impacts and gravitational wave signals. And you can also see here indicated that we want to be in a permanently shadowed region. Now that is for us absolutely crucial because we need the best temperature stability that we can possibly get on the moon. And if it's cold, even better. But the temperature stability is really the key point here. And you find, of course, these regions at the lunar poles, and these are ideal. The moon is the key enabling factor, however, of the moon is that it is seismically extremely quiet, orders of magnitude quieter, several, I would say almost many orders of magnitude quieter than Earth. We have so far only upper limits set by the Apollo missions, but we have models as well, and they tell us that the moon is quieter by 6 to 7 orders of magnitude compared to Earth. And that is really the important feature of the moon, why it might work. Now, the payload is under development, of course, at the level of terrestrial prototypes, putting the sensor unit mostly together. Now, what we propose is that this is going to be a mechanical seismometer, essentially with laser interferomagnetic readout. There are other options, but we are pursuing that street at the moment. And we have this cooled down to 4 Kelvin to be able to profit from superconductors or superconducting technology with niobium material. There might also be other options for that, but this is anyway the main, the baseline design that we are currently following. And that gives us something like, in the end, femtometer per square root of hertz sensitivity at 1 hertz and sub-picometer at 0.1 hertz. And that's what you need if you want to detect gravitational waves. Now, together with LGWA, we now proposed last year Soundcheck mission, which is essentially a geophysical explorer and technology demonstration for LGWA. So that is a single seismic station to be deployed in a permanently shadowed region. And here we target sub-picometer per square root of hertz throughout the decihertz band. Of course, this is really meant, in addition to being a technology demonstration, we have to understand much better the geophysical environment in a permanently shadowed region to have a better, to have more information about the seismic background events and so on and so forth. So, and this mission was now selected into ESA's reserve pool of science activities for the moon. Okay, we also have funded a lunar emulator. That's very tricky to achieve on Earth. So we are going to build a seismically isolated platform underground, more than 1 kilometer underground in the LNGS underground laboratories. These are famous really for dark matter searches and neutrino physics, but we are also having a spot there for this in-vacuum facility. So the goal here is to create the quietest possible platform vibration in terms of vibrations, and then to put the cryogenic sensors on that platform, and then to essentially assess their performance, well, mostly in terms of their vibration sensitivity. And so on these platforms, we will be able to demonstrate these picometer to femtometer sensitivities that we need for the moon. The sensitivity targets are these. Now, just to point out, I mean, maybe you're not familiar with these plots, but in any case, so with that type of sensitivity in that band, you will be able to see a wide range of masses, compact binaries. That means massive black hole binaries, intermediate mass black hole binaries, solar mass black hole binaries, noon star binaries, white dwarf binaries, any mix of them, intermediate mass ratio in spirals. Many of these sources connected to electromagnetic counterparts. And so that is an enormous science case. And of course, that has been known before. That's the reason why very ambitious missions like the SciGo and Big Bang Observer were proposed in the past to observe in that band. The range of observation that we can achieve, especially with the intermediate mass black hole binaries, would be a few tenths in redshift. And that is, of course, making this also a cosmological, not only an astrophysical mission. And that's where we stand at the moment. So we are having already a collaboration of close to 200 members now, working on the payload, working on the science case. And that is, of course, a lot of lunar science as well, not only gravitational wave science. And yeah, that's where I want to stop. Thanks.
So much, Jan. So our next speaker is Yuri Evangelista, who is going to speak about the Lunar Electromagnetic Monitor in X-ray, that is LMX. Really, the floor is yours.
Thank you very much. I will go a little bit in more details with respect to what Francesca presented this morning about the EMM project. In particular, I will show you the lunar electromagnetic monitor in X-rays, or this idea. But I will start from a couple of astrophysical questions that arose in the last years. We got aware that the study of the universe in the time domain has become increasingly important, meaning that we need time-resolved wide field observation on different time scale, from very short, let's say from microseconds or milliseconds, to very long, tens, thousands of seconds. And this kind of observation already are we know that are bringing to light unknown transient phenomena like fast radio burst or other phenomena. On the other hand, as Jan was saying, the detection of gravitational waves and, for example, the discovery of their electromagnetic counterpart started a new era for astrophysics, where we now know that we shall merge electromagnetic observation together with gravitational wave observation and also neutrino astronomy. So the idea is that we need a high performance wide field of view X-ray monitor, which can provide us with prime observation of the violent sky, meaning in the high energy range from X-ray to hard X-rays and gamma rays. what we need a high energy band from a few kV to 10,000, 100 of kV. We need a large instantaneous field of view, which with the goal of observing the whole sky simultaneously. We need a long continuous observation uninterrupted in order also to study variation of long-term variation of sources. We need a very good angular resolution of the order of arc minutes to provide coordinates to optics and observatories, and possibly a better subarc mean point source location accuracy. We need a moderate large effective area if we want to observe transient events, which translate in a good sensitivity. Here I'm using the crab unit, which are common in the X-ray community. Anyway, sensitivity of 10 at -8 square centimeter per second. We need photon by photon capability in order to perform in deep timing and spectroscopic analysis of the events, a good energy resolution, and very good time resolution of the order of microseconds, tens of microseconds, and of course also negligible dead time, especially if we want to avoid saturation for really intense and important transient events. Why the moon? Our moon offers, of course, not atmosphere, which allows for X-ray observation from the surface. Depending on the position of an observatory on the moon, it allows for full sky or half sky accessibility on a long time, a very stable environment, which is good for angular resolution and point source location accuracy, and continuous operation. Of course, the moon also offers a large room for resources like volume, power, telemetry, and the possibility to assemble a very large instrument, too large to be put on a free flyer in a modular way, and also to service the instrument during time. Also, with respect, for example, of high elliptical orbits, which can allow for continuous operation and full sky observation, the moon has a mild radiation environment, meaning that the X-ray detectors can live for a long time with moderate cooling. So the idea is to develop a very large permanent X-ray observatory called LEMIX, based on the coded aperture X-ray imaging, and operating in energy band between 2 and 50 kV. Each camera is equipped with a detector tray made of silicon drift detectors, and is capable of monitoring both from the imaging, timing, and spectroscopic point of views, a very large field of view, more than 2 steradians per camera. The camera is thought to be completely modular. For example, also the backend electronics and power supply unit are integrated in the camera. So that means that the instrument can operate with incremental performance starting already from the installation of the first 1 or 2 cameras, of course, with a limited field of view and limited sensitivity. The goal is to reach a complete dome like the one you can see on the left side, composed from number of 30 cameras in order to have high sensitivity monitoring. And of course, the astronaut is not included in this project at present. This is a representation of the camera, which is the design is we will see is already in advanced state, and as I said, the detector is based on a silicon drift detector, which allows for point source location accuracy of 1 arc minute and angular resolution of 4 or 5 arc minute, depending on the optical design of the camera, and a very good energy resolution, and also very good sensitivity. The resources are quite good. The camera is compact, 35 centimeters, is lightweight, about 15 kilograms, and the power consumption is about 15 watts at present. We are working on this project in the context of the PNRR, which is the Italian Recovery and Resilience Plan. And in the framework of this project, we are now developing the detector tray. Anyway, the whole camera design is based completely on the heritage of the WFM that we developed for the LOFT ESM3 mission for the phase A study, and now also the same design, camera design, will be on board on the XTP Chinese European mission, which shall be launched at the end of the 20s. The project will be completed by mid 25, and these are just a few snapshots of the technology. These are the large area silicon drift detectors developed. This is a very large detector, monolithic, 7 by 7 square centimeter, already developed in a collaboration between INAF, National Institute for Nuclear Physics, and the Fondazione Bruno Kessler in Trento. The readout electronic, both analog and digital, rely on the heritage of the few ASICs, Vega, Lyra, and Orion, that were developed by Polytechnic of Milan and University of Pavia in the framework of the Rexo collaboration. Lyra ASICs will be on board the Hermes constellation to be launched mid next year. It's a CubeSat constellation for high energy astrophysics, while, for example, the Orion ASICs is in the Theseus design. Last point, technological point, which seems simple but is not, is the design of the front end. Being this an imaging instrument, we need a very stable detector plane, so we need to ensure both very low noise in order to reach the required spectral resolution and angular resolution, but also very stable detector plane in terms of thermoelastic deformation, which is very important, of course, on the moon, depending on the site, but the temperature variation could be very large. This is my last slide. These are simulation of a crowded field of the galactic center with several sources that can be observed and imaged in a few kiloseconds. And these are the single camera anticipated performance. Of course, the total performance will depend on the number of cameras and the total design. But as I said, the field of view is very large, very good angular resolution, point source location accuracy. The sensitivity is more than enough to image and perform timing and spectroscopic analysis of transient events like gamma ray burst or X-ray burst or etc. The energy resolution is comparable as an order of magnitude to the best one that you can reach with a CCD, but this is the one important point is that these detectors are single photon detector, so we have this energy position and time information for each single photon, not for the integrated frame. The time resolution also is very good. It's of the order of 7 microseconds, but can be improved to a few microseconds, 1, 2. And also the expected time will be very low for an intense event. So that's all.
Thank you. Thank you, Yuri, for your talk.
Time is good.
Okay, so our next speaker is, I think, going to join us online. Douglas Curie, who is going to give us a review on the design and fabrication of the next generation lunar retroreflector. Are you there?
I don't see him signed in yet.
I don't see you. No, the speaker is not present.
We can move to the next presenter. Have more Q&A time.
So our speaker for now is not present right now online. So we are moving to our next speaker, who is Maria Genzer, who is going to talk about the lunar in-situ navigation and communication mode, LUNINA.
Yes, hello. I'm giving this presentation on the behalf of Harri Haukka, who could not be here this week, and on the behalf of all the other people in consortium also, of course. So, what is LUNINA? LUNINA is a communication, in-situ communication navigation mode for node for Moon, and it has several very important properties. It's very compact, as you will see on the next slide. It is quite small, well, this small. And it's independent, meaning that it can operate independently of other systems. It does it, so it's autonomous. It's robust. It can have very generic interfaces that can be compatible with many assets. It's also location independent, meaning that it's a box that you can drop basically anywhere on the moon where there is some sunlight. Of course, there has to be an analysis like how much sunlight do you need, but if you have at least some sunlight, then you can put it there. It's cost effective because it's based mainly on the other systems that have already been preliminary designed, so you don't have to start from scratch, and it's able to operate 24/7 on the moon. So the LUNINA is supposed to work as communication and data transfer relay for both ground and in-orbit users, and it will also provide a signal for navigation purposes. The platform of LUNINA is based on LINS platform, which we at FMI, together with our partners in Spain, made preliminary specification for mini-pins project that was funded by ESA. And this idea of LUNINA was submitted to ESA in 2022. So I mentioned mini-pins, which is its LINS lunar surface sensor surface package is the basis of LUNINA. I will not go into much details of LINS because there will be another presentation by Ignacio Aruego on Thursday. He will tell more details about LINS. But as you see, it's basically, well, a box that has space and accommodation for different scientific sensors. And in our case, in LUNINA case, the scientific sensors can be replaced with the communication system that we need. So LUNINA, as I said, is based on LINS because LINS concept is very adaptable. And so instead of the scientific sensors, or well, maybe there will be even room for some scientific sensors, but we could also replace them all if needed. The plan is to replace them with Nokia LTE system as the payload. And you have the specifications here on the screen. So it's quite small, but it's scalable, so it can be made larger if needed. The mass of LINS or LUNINA, as we have it now, is about 7 kilos, where around 1 kilo is reserved for the payload, or in this case, for the LTE system. And it is designed to survive on Mars even during lunar night. Oh, sorry, to survive on Moon. I talk so much about Mars that Mars comes into my dreams. It's designed to survive on the Moon, even during the lunar night. And for that, we have several design choices, and I will leave those for Ignacio's talk on Thursday. But one thing I will say, it relies on a European RHU to survive the lunar nights. And for the electric power, it has solar panels and there's a battery buffer. So really it is able to operate also during the lunar night. So what could it do? It could form a communication network and navigation aid. So for example, what kind of services it could provide? It could provide exploration support. So there could be communication relay, data relay. It could provide it to ground exploration missions. It could be placed close to habitation and bases. And it could also provide these services to the lunar orbit and transfer from orbit. And the navigation aid could be provided both for the in-orbit assets and also those that are on ground. And there are several deployment locations that we have considered. So this is the Schrödinger crater as an example. And so preferably these boxes should be placed somewhere on high ground and on the crater edges, so they can provide larger coverage for the communication network. But also they could be placed around moon bases or other infrastructure as needed. And once placed there, you can basically just forget about them. They will work for at least 2 years on moon, or they are designed to work at least for 2 years on moon without anyone basically touching them. And as for deployment, the original idea for LINS, or now Lunina, is to be deployed from a rover. It can be also, the design can be modified so that there will be a standard interface with commercial landers also. And in the longer term, there could be even a dedicated landing system that could bring down not only Lunina, but maybe also some additional payloads. And that is my last slide. Thank you.
Okay, so we will check. Yeah, exactly. So we are going to check again once more if our previous speaker is online.
I don't see them online yet. They're not signed in yet.
I think then we have to move ahead with the question and answer session. Okay, so please, may I call the speakers again on the stage? Sorry, Maria. You again. So we have already one raised hand. Okay, there are many.
It's an LTE system, so it's basically the same system that is now on one of the rovers where Nokia has provided the payload. So it's LTE, it's like 4G basically. I have to say I don't know the frequency right now, but I'm sure it will be made compatible with the assets that are around the moon.
Next question, please.
For the gravitational wave antenna, I was wondering, with the placements of every basically node 1 kilometer away, what's the current plan for the deploying of them actually on the surface and the distancing, and then also ensuring, I guess, I saw the leveling system, but even like securing them on the ground. Is there a plan defined for that yet and a procedure?
So for the moment, we don't believe that the mounting is a major issue, but we will make deployments in lunar analogs to understand that issue really more precisely, as was done for Mars InSight as well. So these issues are of course known, but generally, I mean, of course, it's a complicated deployment. So it has to be done by, I assume, a rover. And so bringing the stations away from the lander, at least 3 of them, spread them out is, yeah, well, we propose it in that way, that you have a rover going and then leaving the stations. But these are parts of the mission that we haven't really looked into detail yet. So, but in any case, about the deployment itself of each station, we will look into this at least from simulation side and from lunar analog studies.
Okay, thank you very much.
Hello. Hello. For the Lunina payload, I have a question. So, what distance can you reach on the lunar surface with the beacon and the communication service?
Well, that detailed design has not been done yet, but it depends on what's the elevation. The higher you get, if you put the package on the high on the crater, then you get more distance, and then, but I think it should be at least kilometers on the surface. So, for example, for the lunar bases or other like lunar rovers that are working on the moon, you could like drop them just like you would drop like these relays on Earth, but drop them with a sufficient distance, and then they would cover some area that you need. And of course, the closer they are to each other, the more accurate it is, and the higher you have this, because they could also work together.
Susan Stewart from the U.S. Naval Observatory. This is a question for probably the last 2 talks. It would be good, or maybe a comment, it would be good for these projects to be speaking with the people that are developing the time standards and also the surface frame accuracies to know what your requirements are, because we're coming together now and we're trying to decide what we're going to be, how we're planning these things. So we've been trying to reach people and the users and the levels that we need to be at. Usually when we ask what are the requirements, they say, well, how good can you get it? So it's good to know and see these.
Thank you for this comment. I just like to add that if you think about Lunina, so the platform itself, which is based on LINS, so it's like pretty much preliminary designed already. And this LTE system, so Nokia's LTE systems, we know that they exist, and the work to actually bring those 2 together is only starting. So this is an idea that was proposed, and we do have a collaboration with Nokia on this, but the practical work of implementing this Lunina is only starting now.
Okay, so do we have any other questions? All right, let's thank the speakers again. Thank you very much.
Sorry, the microphone wasn't switched on. So we'll rapidly move on to the next session, or sub-session, I should say. So I think think then our next speaker will be Jason Hopkins, presenting for John Ware. Is our next speaker here? Excellent. Thank you. So this talk will be about Parsec, which is a lunar communications navigation service using small satellites.
Good afternoon, everyone. My name is Jason Hopkins. I'm with Crescent Space Services, a wholly owned subsidiary of Lockheed Martin. And I'm here to talk about our common navigation service for lunar missions called Parsec. So just a quick background on the lunar market and like what we see near term, midterm, and long term. So in the near term, we're starting to see the takeoff of robotic exploration missions, specifically within NASA, within the CLIPS program office for commercial payloads. You've got the NASA rover under the Lunar Terrain Vehicle coming up. And so robotic missions are starting to take off here, and some commercial missions as well. And then we see as the lunar economy grows in the midterm, you'll start having human exploration on the moon through the Artemis program and the likes, and which is partnered with international partnership agencies through NASA and their partnerships like ESA. And then it expands into, we see it expanding into that commercial growth, where you've got now more commercial companies looking to build permanent infrastructures. You've got long-term human habitation and more frequent access to the lunar surface and lunar orbit. Now with this expansion, there's a few of us that see the need for foundational infrastructure, and that starts with communication and navigation, very similar to what we have here on Earth. And so with that, Lockheed Martin started investing in developing a commercial service company that will be more agile and flexible for starting off with the U.S. government needs, but also the commercial industry and international partners as well to support these lunar missions, with that first infrastructure service being common navigation. So we formed a wholly owned subsidiary out of Lockheed Martin called Crescent Space Services to do just that, provide that infrastructure as a service for missions in cislunar space and on the surface, utilizing the Lockheed Martin heritage, especially with deep space comm, that reliability that comes with that, and then combining that with the agility of a commercial service company. So again, we're developing what we call Parsec, a constellation of lunar satellites for communication, position, navigation, and timing as a part of that, addressing that need. So it is a capability as a service. We do basically equivalent to like a cell phone service. You can buy plans to provide your missions with common nav services. And that service will be available on orbit in 2025. We're going to provide secure, high bandwidth comm between Earth and a cislunar and lunar surface missions up to 100 megabits per second downlink back to Earth. And then we've also got position, navigation, and timing as well for orbiting and surface missions. The Crescent leadership is, we're led by Joe Landon, former Lockheed Martin executive. He's our CEO. Myself, running Vice President, Strategy and Business Development, and Lindsay Papsadero is our Director of the Parsec Lunar Network. So what is Parsec? It is a commercial satellite network, built by Lockheed Martin as our subcontractor, if you will. And it is providing that communication relay between Earth and the moon, and that PNT, position, navigation, and timing service. It's built off the Lockheed Martin Curio bus platform line. So we have two of those, leveraging some existing heritage from some of their lunar missions, as well as some of the deep space comm missions, for example, some of the Mars comm relays. We're partnering with commercial ground station networks. The intent is the service is to be agnostic to commercial ground station providers. So we have global ground station coverage for any ground entry point. Again, looking to roll this out in 2025. So the network, 2 satellites intended to go into an elliptical orbit around the moon, focused more so on the South Pole. So we'll have, with the second node up, we'll have 24/7 coverage of the South Pole. Again, designed right now to support the human exploration missions that are intended to land down in the South Pole regions, and the South Pole exploration robotic missions. We do have, it is a mesh network, so the capability to add more nodes as the economy and exploration grows to service different latitudes on the moon. If we need to, as more things approach the North Pole, we'll look to adjust the network as appropriate. And then again, it is a subscriptions-based model. We do have different plans for different mission types. We look to work with any mission partners to provide them an affordable capability to meet their mission needs, to accommodate their swap constraints, providing you high data rates back to Earth for your mission data at a fairly reasonable price. And pricing is available upon request. So happy to talk offline if people are interested in understanding pricing and service capabilities. Oh, that was fast. That's it. My contact information. Happy to take any questions in the time frame or afterwards.
Thank you very much, Jason. You're well within your time limits.
It's high-speed comm.
I think we could just move on to the next talk and do the questions collectively, if that's okay with you, because then we can catch up with the room above. Yeah, thank you. Yep. So moving on to our next speaker. I'm sorry, I briefly have to consult our schedule. Next speaker is Matthew Christie, working on Lunar Pathfinder, which is a project by Surrey Satellite Company. Also aiming to offer a communications relay service in the not too distant future. Yes, of course. Yeah, you can use this one.
Good afternoon, everyone. Yes, I'm here today representing Surrey Satellite Technology in the United Kingdom. I'm going to talk to you about Lunar Pathfinder, which is our upcoming communications relay satellite. So a bit of background, a rejuvenated interest in returning to the moon has unlocked this emerging lunar economy with bullish forecasts of revenues in the hundreds of billions over the next sort of couple of decades. And this sentiment is being matched by record levels of government funding towards space exploration, which is a trend that's expected to continue into the next decade as well. So to build our business case for Lunar Pathfinder, we conducted a number of internal analyses and identified some trends. So we see a slow increase in the number of missions increasing year on year, driven by successful lunar landings, more regular lunar transport opportunities, and a maturing lunar infrastructure, which will augment additional services off the back of these. In terms of mission types, we're seeing a high volume of CubeSat missions due to their sort of low cost and ability to be used as of both rovers and landers due to their utility for both crewed and non-crewed missions. In terms of data, we are looking at growing data requirement demands, really jumping within the next decade and just continuing into the 2040s, driven by more capable technologies in terms of data rate and data volumes, more durable technologies due to the ability to survive lunar nights, and more ambitious missions such as in-situ resource utilization or surface stations, which will be naturally more data hungry. In terms of locations, great focus on South Pole and far side regions due to their sites of scientific significance and also the detection of a relative abundance of resources like water and other volatiles, which can be used for the long-term sustainability of the moon. So we've identified an emerging lunar economy. Why do we need data relay? Why can't we just use sort of the incumbent solution of direct Earth communications? When we consider DTE as an independent solution, a few challenges arise. The first one being line of sight. So direct Earth requires a direct line of sight between the Earth ground station and the spacecraft or lunar asset that they want to communicate with. This is impossible on the far side of the moon. It's limited at the polar surfaces, which we've seen as a hotspot of activity, and can be affected by lunar topography like bridges or craters. Another challenge that arises is in terms of availability of the direct Earth networks. And this growth in missions over the last few years, and which is expected to grow, has resulted in these networks being routinely oversubscribed, and this is only likely to sort of continue. Our third point here is to do with flexibility. So user requirements, depending on the mission phase, will be completely different. If you think about a lunar lander during orbit operations, their usage of a communication service can go from minimal compared to when they're during descent and landing, where they will be completely different. Trying to accommodate this flexibility in DTE network schedules, which are often scheduled weeks to months in advance, can be very difficult. Additional benefits can also be delivered through data relay, including reduced operational costs by optimizing the use of ground stations, lower swap property terminals that, versus those that are required for direct to Earth. Communication performance can also be enhanced, such as improved data rate or increased data volume versus those that are achievable through direct to Earth. Using something like Lunar Pathfinder as a secondary solution will help to retire some risk by using it as redundancy. So helps to sort of de-risk some of these missions that operate in the lunar environment. A data relay will also solve the line of sight issue that I talked about in the previous slide, which will improve the exploration capability of something like a lunar rover, which can go to the far side. It can go outside of the proximity of its lander. It can go into craters. So just really increasing that exploration proximity and value from the mission. And last but not least, we have interoperability, so flexible integration with the rest of the lunar ecosystem to really maximize the impact from missions. So Lunar Pathfinder is due to launch at the end of 2025, with services beginning in early 26 after a short commissioning period, due to last for around 8 years of operational lifetime. Lunar Pathfinder will operate in elliptical lunar frozen orbit, or ELFO. This is really to focus on a long duration coverage of the South Pole, which, as we've identified, will be a hotspot of lunar activity. SSTL will also be partnering with the ground segment provider KSAT in order to kind of combine the strengths of both direct to Earth and lunar data relay to really leverage the strengths of both of these solutions. So we have some very exciting news this year. We've found out who will be delivering Lunar Pathfinder to its orbit. So through NASA's CLIPS CS3 task order, Firefly Aerospace will be delivering Pathfinder to its orbit using their Blue Ghost lander. So once Pathfinder's been deployed, Blue Ghost will then land on the far side of the moon, and one of the hosted payloads on board, Lucy Knight, which is a NASA radio telescope on the far side of the moon, will begin its operations, and Lunar Pathfinder will actually serve Lucy Knight with these data relay capabilities. So Lunar Pathfinder will communicate with assets through the Moonlink in S-band using a proximity 1 protocol, which allows it to communicate with a number of different assets within the same coverage area. This data will then be relayed back to Earth in X-band. In order to maximize the scientific output of Lunar Pathfinder, there will also be a number of hosted payloads on board from a couple different institutional partners. So NASA will provide the laser retroreflector, which will be used to carry out ranging experiments to inform future lunar missions. A GNSS weak signal detector from the European Space Agency will allow us to investigate the potential of Earth GNSS signals to be used to augment lunar navigation. And our third hosted payload is also from ESA, and this will be a radiation monitor. So we will be investigating the characteristics, the radiation characteristics of the orbit of Lunar Pathfinder. So in terms of our service portfolio, we kind of have two boxes here. So if you think, if we're looking at the middle and the last box, we will see baseline services, which will be provided as soon as Lunar Pathfinder becomes operational, and our future development services, which will be implemented somewhere down the line of Lunar Pathfinder's lifetime. So all the communication services will work on a store and forward architecture. If we look at our first one, our autonomous service will allow the contact between Lunar Pathfinder and the customer asset to be automated, allowing the capacity of Lunar Pathfinder to be optimized. Our schedule service is for those who are looking at more dedicated offerings, so they can decide on the time and the length of the contact. Pathfinder can also be retasked in the event of an emergency in order to assist some assets in a state of stress. So down the line, yeah, we're looking to implement our expedited data transport service. It will be the highest level of performance, lowest level of latency. Backup service will be for those where Pathfinder is maybe the secondary communication solution. So talking about earlier retiring some of that risk. And point-to-point, which will allow a lunar asset to communicate with another lunar asset through Pathfinder, so no need to involve an Earth ground station. And to just catch you up quickly on some of our activities, so we have a mission builder app, which is available online. Potential users can input high-level mission characteristics and receive a forecasted coverage and performance report. Our service guide is also available online, so it just delves into deeper detail about some of the services that I've talked about today. And just a note on Lunar Pathfinder's namesake. So it's actually gained this from being the first node in what will be ESA's Moonlight initiative. So Moonlight will be a constellation of lunar orbiting satellites that will provide enhanced communication performance and navigation services as well. So very exciting times to be involved in this space. Thank you all for listening. And yeah, please get in touch if any of this sounds interesting to you.
Thank you very much, Matthew. Excellent. So nicely on time. Let's quickly move to our third talk of the day. Might I invite our next speaker, Mark Robinson, to come up? Mark will be talking about ShadowCam, which is an instrument on board KPLO, which has yielded its first results. I have a timer for you. Would you like to use the mobile microphone or the?
Oh, yeah. Thank you. Okay. All right. Thank you very much. Hello. I'm here to talk about ShadowCam, which we luckily went into orbit in late December on board this beautiful spacecraft, KPLO, built by the Korean Space Agency. Really awkward. I guess I could look right here. Right? Okay. There's a picture of the spacecraft, and our goal is to take pictures in permanently shadowed regions, which is challenging. I'm also the PI of the Lunar Reconnaissance Orbiter camera, and it's always been a little bit of a frustration that we're mapping the whole moon at sub-meter resolution, but we just can't get good pictures inside permanently shadowed craters. So to solve that, the clicker. Oh, okay. Did it work? Look at that. Okay, just a quick mission overview. We heard a little bit about KPLO and the gamma ray spectrometer this morning in the first session, but we're in a polar orbit, 100-kilometer altitude. Of course, 100 kilometers circular on the moon. It's not, because the moon's gravity field is so lumpy, but we go up and down. It's really 80 to 120. The mass of the spacecraft is 665 kilograms fully fueled. And then, after you burn the fuel off, it's 406 kilograms. We were launched on a Falcon 9 last summer, a very hot and humid day. And we went into I should have put mapping orbit on 31st of December. I think we actually went into elliptical orbits 3 or 4 days before that. The objective of the mission is, for the Korean Space Agency to develop their lunar exploration technologies. and do a lot of great science while we're there. Topography, environment resources, so on and so forth. And they're demonstrating a really cool technology, which is a disruption tolerant network, kind of like the internet for space. It worked. Okay, here's a graphic of the spacecraft. I'm not going to go through all these payloads because I don't have time, but suffice to say there are 6 payloads on board the spacecraft, one of them being ShadowCam. I had a picture of flight hardware. I love seeing flight hardware, so I can't resist putting pictures in. It's a any of you who are engineering, you'll chuckle about this. It's just a simple modification, to lunar reconnaissance orbiter camera, but nothing is ever simple when you're building things to go out into space. And if I had a bunch of time, I could tell you stories about that. But our objectives are to map albedo patterns in permanently shadowed regions and interpret their nature, investigate the origin of these anomalous radar signatures that were seen from previous orbiting radar assets, document and interpret any temporal changes that we may see, map the morphology of the permanently shadowed regions to search for any landforms that may be indicative of the presence of ice in the near surface. By near surface, I mean top tens of meters, and provide hazard and trafficability information within PSRs for future landed elements. Okay, the way this instrument works, I guess if I point here, it won't show up there, will it? Is we take advantage of the sunlight that's over here, comes in, hits a little area on the wall of a crater, and then that light is scattered down inside the shadow region. So the camera is about 200 times more sensitive than the LROC-NAC, so that we can take pictures in these dimly illuminated regions with a pixel scale of a little better than 2 meters and a signal to noise ratio. On average, of course, it changes depending on the lighting of a particular crater, or something like 100. So we get really beautiful images. Here's a picture just to show that I'm not just making it up. What we're getting right now. This is a steep wall of this crater inside the floor of Varshavinsky near the North Pole. Light was coming from this direction, illuminating that wall and bouncing down into the crater, and we're looking at the steep wall on that side. You can see these albedo patterns, and you can see small boulders. We're getting down to the detection limit. So these are 5 or 6 pixels across 10-meter boulder right there. So the camera is working beautifully. Here's just an example of how confusing the lighting can be. This is the rim of Marvin Crater, which arcs across the scene here. On the left, where it's all white, that's ground that was illuminated when we took the picture. We cannot image illuminated ground because the camera's too sensitive, it saturates. So we can only image inside shadowed regions. That upper arrow that's pointing this way shows that crater. If you look inside that small crater, that the illumination is on that side, and then once you go over down into Marvin Crater, you can see the lighting is coming from the opposite direction. So it gets really confusing when you're not used to looking at pictures like this. And then on a big crater, like say Shoemaker, when you're in the center of the crater, if you're a cube sitting there, you can get lighting, even lit lighting on all 3 sides of the cube. If you're further back, away from the illuminated source, changes dramatically. It's more normal. If you're up near the illuminated wall, you can get illumination on all sides. The craters look really weird. So I caution people in the science community to start looking at these pictures and get used to them. We've been very slow to release because we've been super busy, but we'll try to get more images out so people can start training their brains. One thing that we've done recently is we went over beta 90. We acquired a bunch of images in equatorial areas, over the terminator, so they have the similar lighting that we see at the poles, and you can compare them to normally illuminated images that we see with an arrow angle camera. Okay, identifying albedo boundaries, that's one of our goals, but we knew it was going to be difficult because as the phase angle increases, okay, as the phase angle increases, you start losing contrast. And of course, we have something similar to very large phase angles in permanently shadowed regions. So one of the first things that we did is we got very lucky when we first turned on the camera. A few days later, we flew over the L-Cross impact site. And we were hoping to see something that looked like these previous impact events, this or Ranger 7 right there and Paul 14, because the crater should be about 20 or 30 meters into diameter, depending on the inputs to the model. But when we got into Cabeus crater where it impacted, no sign of the impact crater. So it could be that the estimates of where it impacted are way off, but that's not really plausible because the work was really good. I think it's just that we're in a very challenged area. It's a very large permanently shadowed, one of the largest permanently shadowed regions on the moon, Cabeus crater. And one of the that's the reason it's one of the coldest. That's why the impact is there. We're just not seeing albedo contrast boundaries there. We're going to keep trying. Every time we fly over, the lighting is coming from a different azimuth. So, we have to kind of stay tuned for that one. But, just suffice it to say, the point is here, it's challenging our goal of mapping out albedo boundaries in some of these permanently shadowed regions. Thank you. Okay, super successful added bonus is we've been collecting stereo observations, which is incredibly important for mapping out, these, I was mentioned, landforms that may be indicative of ice in the regolith. Because if you want to know the depth to diameter ratio in the slopes, it's really difficult to get that from just a single image. So the CARI team has been totally awesome, and they've been slewing the spacecraft. So what we'll do is we'll do a nadir image, and the next orbit is slewed, the next orbit a nadir, and we've been collecting these test stereo observations. It was never part of the original plan, not part of their operational plan, but they understand the value of this. So, we've been collecting quite a bit of so-called test data, but really awesome science data. And we're really hoping during the extended mission that we'll get, time to, after we've looked at all the data, to make follow-up observations where we've made discoveries. We've also been imaging the near side of the moon under different earthshine conditions very successfully. You can see there's the central peak of Aristarchus crater. It's very bright. Robert Wagner has a poster that's covering this. So I invite you to go look at that. I don't want to spend a lot of time on this. But one of the things that I've been saying for years is if you have a rover on the near side, you can use the night. The night is your friend on the near side. It's not something to be scared of and to hunker down and survive. The night is there for your exploration. Okay, I think I'm doing good on timing. Summarize here, the shadow cam is performing nominally, which is engineers, know that means awesome, right? KPLO is performing nominally. The CARI operations team is really going above and beyond. They're just totally helping us maximize the science. I really appreciate it. Spacecraft has enough fuel on board for 1 or 2 years of extended mission, and this could come in very, very important science for looking at new craters that may have formed, during the mission or landslides that may have happened. And our data will go to the PDS in early 2024. All right, thank you for your attention.
Very much. Thank you very much, Mark. That was a very interesting peek into some of the darkest places on the moon. I would like to invite our next speaker, Daewon Jung, who will be talking about the mission that the previous instrument is on, the KPLO, and the first science results coming from there.
Hi, my name is Daewon Jung. I'm from the Korea Aerospace Research Institute, CARI. I'll be giving you a talk not about any of the payloads on KPLO Danuri, because I'm not part of any payload team. I'm actually part of the attitude control team. But as you can see, we can get a lot of data, a lot of interesting data out of Danuri. So briefly, Mark Robinson gave a very nice overview. So basically, this is the mission launched on August 4th. Recently finished commissioning. It was likely to be an extended mission. So this is the route that Danuri took to the moon, very long route. This is the first flight from the Luti camera. A very nice Earthrise. image and one of the simulations that I did to match it. So KPL is 5 sciences, not including the DTN payload. That's a technology demonstration. None of the results are widely available yet. Probably a lot of them are under embargo. But KPL does generate a lot of telemetry, housekeeping telemetry, attitude control telemetry. So this provides a lot of insight into the spacecraft dynamics and also the surrounding environment. So this is kind of a lot of engineering stuff, but as you can see, it will lead to some science. So KPL spacecraft is controlled by reaction wheels, but we do get a lot of momentum built up in there because there's a significant amount of external disturbance torques. So these tend to shake the spacecraft very minutely, but over the course of many orbits, it tends to build up. And there's another thing that we don't quite, we know the inertial parameters. You know, the inertial parameters are a moment of inertia of any solid object. We measure them at the time of launch, before launch, but we don't quite know them exactly at the moment. So can you know any of these? Can you measure any of them? Well, so I went about and did that. It's just rigid body dynamics. So the main sources of disturbances that shake the spacecraft in lunar orbit are there's a solar array drive assemblies. The spacecraft has 2 wings, solar array wings on symmetrically mounted. These generate a significant amount of disturbance torques because there's stepper motors in there. And also there's a gravity gradient that's caused by imperfectly centered center of gravity on the spacecraft, a little bit off, but in turn the gravity pulls on the spacecraft, creating a torque. A little bit smaller than that is solar radiation pressure caused by photons from the sun, and also photons from the moon, which is lunar radiation pressure. And even smaller than that is gravity terms that are caused by well, as you know, the moon has very imbalanced gravitational field. There's also an antenna that moves on the spacecraft normally, but for this study, the antenna thankfully stayed still. So we use an incentive Kalman filter to figure out the moment of inertia. Fortunately, there was a lot of data, so we found some data where it can make the filter observable. Unfortunately, the telemetry interval is very coarse, 1 hertz, and some of it is even worse, like 0.25 hertz or 0.1625 hertz. So we had to do a little bit of interpolation. Well, this is basically just an incentive Kalman filter. So we'll talk a little bit more about the major sources of disturbance. So the solar radiation pressure, which is caused by photons impinging on the spacecraft, mainly we treated the spacecraft as a plate model. This is a very standard equation that we use. We also modeled the lunar radiation pressure. So we modeled the moon as a kind of a plate model using the LRO diviner temperature data. So the hot areas they look hot, they're red. And in this particular data, we have the spacecraft starting to orbit above the hot part, and then going back behind the cold part, which is the shadowed part. We also assume a gravity model at first, but as you'll see, as I'll explain later, our data can show that this gravity model it's kind of observing the gravity model as well. So for this study, we assumed the Grail 1200A model. I know there's a more recent one, but so up to order 10 only, because MATLAB It gets really, really slow if you do any more than that. So this is the range of telemetry data that we use. It's from February 14th of this year, about 2 lunar orbits, starting from the far side, and then 1 orbit, 2 orbits later, ending on the near side, which is in eclipse. Dark side, a dark near side. So we did a little bit of pre-processing using an in-house parser and a little bit of interpolation, some data massaging. So we measured the moment of inertia first. So we've picked some data. We didn't intentionally slew the spacecraft to do this, but luckily there was some data that showed some maneuvers in the z-axis, the x-axis, and y-axis, which gives us a complete range of observability. So, and the bottom plots show the moment of inertia converging. Well, you might argue, why is it oscillating? That's because the solar rays are rotating. So as you can see, as you'll see later, however, I can subtract that out. So this is just the inertia of the solar rays. And I can subtract the values out and compare them with the moment of inertia that we measured on ground before launch, which we only did for certain fill fractions of the fuel tank of the propellant. So so we started with 40%. And the converge value is slightly lower than that, indicating that we have a little less than 40% fuel life. It's pretty close. The off-diagonal turns are nearly the same. So method works. And then we look at the solar radiation pressure during eclipses. There's no radiation pressure. Lunar radiation pressure looks good, and we start off in the hot side. You see there's a very large radiation pressure component. Then gravity gradient torque. These are high order gravity gradient torques. We actually get something that looks interesting, looks plausible, I think. We start out around here, where there's a lot of gradient here. This corresponds to this part. So I think it might be plausible. As you know, the gravity is very delicate to measure. So, but results seem not so off. The magnitude is pretty good. And one more thing, we got data, so we can work out the gravity coefficients backward using a neural network. So these are spherical harmonics. You know this from, they're arranged in a lower triangular way. And we can estimate them using a neural network that's kind of arranged in the same way. It looks kind of similar. So we stack the, so we make the network shape kind of similar to how the spherical harmonics would be arranged. It's getting larger and larger as you get towards the end. And we input the position and the normal of the position and the gravity torque that we got from the beginning. And then what we get is the spherical harmonics out. So I don't know, it might be overfitting, probably, but it's an interesting way of doing it. So in conclusion, we can get some very interesting results from looking at just the telemetry of KPLO dynamic. Thank you very much.
Thank you, Dawood. If you wouldn't mind sticking around, can I invite the previous speakers to come up here as well, so we can have our collective round of questions. So I'm sure there will be a few questions from the audience. Who would like to start? Do we have a room microphone? Yes, we do. Excellent. All right. Are there any questions yet? Yes, I see someone in the back.
Again, this is Susan Stewart from the U.S. Naval Observatory. My question is for Parsec. What are you planning to use as your time source for your navigation constellation? And are you going to ensure that's inoperable with the other constellations like Moonlight and NASA's LunaNet? Because we don't want accidents having different time sources. We're trying to model the time sources now, and we're seeing a lot more than the 56 microseconds a day. And we're still trying to understand that. I'm just asking if what you all have looked at in that area.
Choice of time source for Parsec.
So we are exploring atomic clocks right now, which the appropriate card that we could use on board. So we'll have to we can follow up with you offline, but we are planning on being LunaNet and Elkern's compliant. And then we're also working with other U.S. government agencies on this as well to make sure we do have a compliant. I'll get with you offline when we have a product.
Right, thank you. Any other questions from the room? Yes. Microphone is on this.
Thank you. So a question to Mark. If the regolith in the PSRs had ice in it, you might imagine that the crater morphologies might be different. I guess you must be looking into that.
Yes, we are.
Are you allowed to sort of say anything about it?
We're looking very closely at it.
It's a work in progress, I gather.
Yes.
Right,
The question,
go ahead.
Yeah, thank you. The question to Mark, did you detect the L-cross impact? Anything from the L-cross impact?
Bernard, you weren't paying attention to my talk. I had a whole slide on that. Now we've looked very carefully, but we have not found it. Right? There's craters there, but there's nothing to make it look unusual relative to the other craters in the area. So either the estimates of where it impacted are wrong, or we've completely suppressed, because it is challenging lighting the albedo you would expect to see there. But I don't even see a sharp rim. So that's a little bit an answer to your question, right? I don't know. I believe the estimates are good, so I don't think it's a matter that the impact. I think they're good a couple hundred meters. So no, we have not found it, but we'll keep looking because the light changes. Cabeus is one of the most challenging large PSRs on the moon. It's very photon challenged.
All right, thank you. Further questions?
To these comm guys, could you speak a little bit to the ground, on the Earth, their side of it, and how resilient it is to weather and storms? And are you using pre-existing assets? Or are you building new assets?
Sure. Yeah, we're using existing assets currently. Again, like with a lot of the global ground station providers. So we will have our pick of the litter for ground station and true points that will not be obscured by weather.
Okay, so you're totally with that.
Yeah, I was going to say I can't add too much more. As I said in the slides, yeah, we're working with KSAT. They've got a global network, existing assets, providing that coverage for us as well. Yeah.
All right, thank you for those answers. Any other questions? If not for now, think on it. Oh, I see one. Go ahead.
Hello, Isacco Preto from OHB Italy. For Lockheed Martin, and what band do you provide the service to the lunar surface for the communication and for the navigation parts?
So to the surface, it's S and Ka band, and then back to Earth, it's Ka and X band. But the Ka band is our primary downlink back to Earth for the high data rates.
Okay, and for the navigation, do you have a different polarization than for the communication, or it's
So can't get into too much of that, but I can tell you that I mean, it's Doppler ranging right now. So.
thanks.
Yes, another question from one of our.
Another for the comm guys. This is fascinating. I'm really interested in it. You didn't really talk about how much power you need from the surface. Like, can a little rover with a 1-watt transmitter talk to your satellite, or how much power needs to be coming up for both of you?
Can't put a quantity on it, but we are sort of working with user terminal providers that will be able to work with customers providing these terminals for different assets, rovers, landers, orbiters, and yeah, we're going to make sure that these terminals can talk to Pathfinder. Yeah.
The goal, though, is to minimize the swap that's required from having to go direct to Earth with any reasonable bandwidth, especially with the amount of data we're expecting customers to have. And so it does reduce the swap that is required on the surface to now connect to a relay. We have to send data back to Earth. But yeah, we'd have to get offline and get just do the link budgets and tell you what the sizes would need for different bandwidth.
Because the other effect, yeah, the other thing is that there are some pretty sensitive ground stations on Earth as well, right? And on the satellite, you have a smaller sensitivity in principle. So that's interesting to work out. I would also like to hear. I see another question here. Yeah. Okay, go ahead. Yeah.
This builder tool that Matthew talked about, you can put in the characteristics of your user terminal in terms of the G over T of the antenna and the power and so on, and it'll tell you the data rate that you can do because it's a variable data rate.
All right. That helps. Thank you. I might slip in a question of my own, actually. So I come from the radio astronomy background, and I am very interested to hear if our telecommunication services have taken into account any self-generated emissions that might interfere with the radio quietness on the lunar far side. Has that been a factor in the design of your platforms, or is it still the Wild West and are there no rules to speak of? Could you maybe provide some comments on that?
I'll let you go first. So we've obviously assessed ourselves to make sure we don't interfere with ourselves and other missions. I mean, we all are intending to be compliant with the standards out there. I know there's a mission, that Farside mission does have a radio silence requirements in their band, which I think everybody will be inherently compliant with. And then the other piece to this too, we have already filed with the FCC, the Federal Communication Commission in the United States, and then they're working with the international international community on frequencies and allocations and uses and licensing. So so we are starting that process to kind of get ahead of the really helping them understand what's going to be required from licensing and regulation of the frequency uses on and around the moon. So.
Yeah, my answer's not too different. I mean, we're well aware of the potential of the far side for radio astronomy. We're well aware of the shielded zone of the moon and those requirements. I mean, as you saw in our slides, our first user will be a radio astronomy telescope, and so yeah, we have it built into our concept of operations and are well aware of it.
Yeah, I figured I'd ask it because these rules have not been completely worked out, right? And so this is still a little bit of an unclear time in our history when we have to settle on a definitive set. I think we have reached 4:30 on the clock exactly. If there are no further questions from the audience, I would like to conclude our session here. Please give our speakers another round of applause. And I would like to hand the baton to our next Chair Gabriele. Oh, I'm sorry, there is a coffee break. Excuse me very much. Yes, indeed, there is time. I think the scheduled time for the coffee break is half an hour, but maybe we should shorten that a bit, right?
So we will have a half an hour coffee break and then please reconvene in half an hour. Thank
Hello, Wayne. Can we do a quick audio check?
We can. How are you?
Loud and clear.
That's very good.
Thank you. Eduardo, can we check your audio as well?
Yes, I'm ready.
Yes, we can hear you. Thank you.
It's okay?
Yes, and you can share your screen when it's your turn to speak. That'll be easier.
Okay, good afternoon. I like to start the session this afternoon after the coffee break on the software on lunar exploration. The first speaker is Wayne Noble, Lithospace, a unique cloud-based lunar geochemistry data platform. Wayne is already connected. Can you hear me?
I can. I'm just going to try and share my screen.
You have 10 minutes. I will tell you 2 minutes beforehand.
Okay. How are we going? Can you see my screen there?
Yes. That's
Okay. All right. Let me get going then. Now, sorry I can't be there. I'm stuck in Australia. I will be in your town in 2 weeks' time, but I couldn't bring my plane forward. Now, today I want to show you we're a software development house. And as a bit of a side project, we thought we'd sort of dabble in some space software. So I want to show you that today and let you play with it if you'd like. So we're a spatial data company, and we predominantly collect data and display it for the earth sciences and universities and mining companies. So in showing you what we've done for the space and lunar, we wanted to show you what we do on Earth, because many of the things that we do with our Earth data, we can do with the moon data. So, and of course, lunar samples we have less of, but we're seeing that there's a lot more future ideas about collecting more samples. So we feel that our platform is a good place to start storing some of this data. So for Earth, we provide clean, standardized data, and we mine that from scientific literature, or we get it directly from machines that produce data in labs. And we store this in a relational database in data models that we've designed with some experts that contain all the metadata, so you can analyze this, the information that you're collecting. And on top of these models, we put our UI, and you can see there's a picture of there of Australia with some, that happens to be some Vision Track data in that picture. So this is just an example of one of the data models. You probably won't be able to see it that well, and that doesn't really matter. But what it's trying to show that we've just got a structured database that you can put data into. And we've also got, we can ingest data either using Excel spreadsheets or via an API. So it makes it easy to get data into our system. And I'll just quickly show you a few pictures of some of our Earth-based data. So this is geochemistry data set that's in Western Australia. And that's just showing the nickel highlighted, and you can mouse over information and find out more about it. You can do things like this is a picture of some PNG geochemistry data, and that's just our contouring tool. So you can actually get a better picture of the distribution of the elements by using tools like that. And then we've got tools such as drawing swath profiles, so you can see the data in its sort of spatial context with, elevation. And then, of course, you can start plotting them in fairly standard plots, and you can see this is geochemistry data, and they're just using things like rare earth plots and trace element plots, and you can compare them. You can see that we've got a normalization in the chondrite there, so you can start comparing, looking at the data and looking at it more in depth. And we've got classification plots up the top there, like that you can start classifying rocks. And this is another type of data, just to show that we just don't do geochemistry. This is vision track data. And this is just showing that you can select multiple populations. And I've selected different populations down the east coast of Australia there to compare them. And you can see that they all have different characteristics there. So we can do all those things. And as we were doing, collecting all this data and writing this software, we kept on seeing articles such as this and hearing about Artemis. And we're going, well, you know, we collect data, and so why can't, what can we do in this space to sort of get involved? So there's no reason why we can't look at data from space or and on the lunar surface. There's, especially the old data that we've had a look at from the lunar and Apollo missions is all geochemistry data, the rocks brought back to Earth and then analysed in labs. So it's exactly the same sort of metadata as we have for Earth samples. And so we decided to create Lithospace. So we're using existing projections of the moon and its geology, and then adopting that into our system, and then using all the tools that are available in our system. But of course, wasn't particularly easy. It's not like the space data is in a beautiful relational database form, and you can just put it into our system. We had to go hunting it. You know, some of it was in PDFs, so we had to strip it out of the PDFs. We also, we could find the locations of where the landing craft landed. That was quite easy, but then where the astronaut took the rock from was a different matter. So we had some students from one of the universities here that were doing a space science degree, and they came and helped us, and they found a lot of the data. So we ended up putting it in our system. So I'm just gonna, oh, sorry, I'll just go back to that. So you can see there, you know, that's just showing you the samples in our system essentially, which you probably have all seen those locations before. So this is just a little video. Hopefully it comes through okay. So you can see, you can view the data. It's not too many points in our database, but we're hoping over the next decades that there'll be lots more. Of course, these are the lunar craft. So, you know, you can put things like the images in there. So when you mouse over it, you can see that kind of information. That was viewing it as at a sample-centric view, but now we're looking at the geochemistry view. We can select those, and as we saw for the Earth-based samples, we can start looking at the trace element plots and the classification plots. You can see that all of those samples there are quite primitive, but you're not really seeing anything new here because it's data that's been around for 50 years, but it's more showing how we can put this data in quite quickly and then start playing with it. And you can see that we've put the USGS geology in there. So then you can project the samples on that and see where the samples are in the context of the geology. Oh, that's going to play again. I don't want it to do that. So here we are. This is just a more detailed look at the lunar samples from 16, 20, and 24. Again, they're sort of, the samples are plotting down in the primitive, so they're primitive basalts essentially. But all of these plots, you can change the axes, and you can, so in this plot up in the top right, you can plot whatever elements are in the system against each other. So you can start to invent your own stories. You can start to look at this data in other ways. Because it's in our relational database, it makes it easy to compare different things. now I don't have too long. So I've only got a minute or so left. So we've got the, you can do the same thing with the Apollo data. There's a bit more of a spread in the data there, which is interesting, but it's showing the same sort of things. So we figure that more data is coming over the next few years, and even this afternoon I've heard a lot of you say such things. So we feel that the platform we're developing, that the data can easily go into that, and then you could start using it to start to understand the data in different ways. So it's anyone can go and use this software. It's free. It's just an offshoot of our main software. So we're not charging anyone for it. It's just community use. And it'll be coming out in July. We're probably going to change the URL to be called, it'll be called Lithospace or something like that. But for the moment, if you wanted to go and see it, you can go and visit it, that URL. Thank you.
Okay. Thank you, Wayne. Please stay connected for the question later on.
Sure.
Okay, next speaker, Igor. Yes. Improving recognition of planetary materials with the revised ESA Pangea mineralogical toolkit. You have 10 minutes. I will call you 2 minutes before.
Hello, good afternoon. My name is Igor Drozdowski, and I work at European Space Agency at the European Astronaut Center as an expert scientist, and where I'm supporting development of this particular Pangea mineralogical toolkit. So to start, I would say that this is actually the main goal of this project was originally to develop a set of hardware and software tools which allows real-time recognition of geological materials. And this is, of course, a team's effort. And our Caves and Pangea team consists of scientists, hardware and software developers. We also have people who are involved in the training of astronauts, instructors, so experts in geology, planetary science, mineralogy. And we also have people who are actually doing very important work of working in operations, specifically ground support operation, both for robotics and the human operation missions. And that is allows us to combine all this knowledge, all these skills together to develop something new. My talk would be only on this particular project, but this project as a part, as a model of a tool that we would be presented on Thursday by Leonardo Turchi, which has a name Electronic Field Book. And these are tool set that is much more broad and includes different models. The Pangea as a program would be also presented on Thursday in the talk of Cesco Sauro from University of Bologna, who is the director of Pangea. So let me start by saying that in our view, real-time, non-destructive and accurate mineralogical analysis will be critical in the future space exploration missions, particularly missions which are related to the future human and robotic explorations for the moon and other planetary bodies. And we already have many experiences and many examples where the rovers, for example, are equipped with different types of analytical instrumentation. However, when we are coming to the human exploration, there are a few peculiarities. And one of these is a time critical. And the time critical, it's very significant constraint for this kind of, let's say, operations. And one of the common examples, what I would say that in our view, we think that real-time usage of a portable spectroscopic spectrometers would be extremely valuable in the future surface operations and the future surface missions such as the Artemis. It has been already stressed in the different workshops and including in Artemis science definition report that have been already shown, but we need this kind of tools. And we are working on it for quite some time, so I think it would be a good time to present for you what we actually developed so far. So as I mentioned before, this tool set is not just developed now. We are using part of this tool set, what we call Pangaea Mineralogical Tool Set, during our Pangaea Geological Field training, for which I originally is designed for astronauts and then was also added in our as in our trainees, also were developers or engineers, aerospace engineers, or developers of future space mission. What we came after usage of this kind of analytical spectrometers during the Pangaea Pangaea campaigns is that we quickly realized the commercial off-the-shelf spectrometers and commercial tools what exist has its own limitations. In our view, we quickly realized that in order to achieve fast and reliable, let's say, recognition of different minerals, and also in order to provide this information in real time, not only to the crew which are next to the instrument, but also to the scientific support room, we need to develop in the same time and test at the same time as working together, three different important parts. One is a portable spectrometers, which needs to be properly configured and to be able to operate with the software in real time. Second, all the reference information what we have, such as the catalogs, petrographic catalogs, all the meta information which are essential for identification of minerals needs to be also already specifically selected and customized for specific instrumentation. And of course, reference archives. If we're talking about spectroscopy, we are talking about spectral archives. Though our idea is that it needs to be really worked really well with the type of instrumentation what we have. And finally, mineral recognition software. So we started with a common software which comes with each of instrument and finished up developing our own machine learning based software. And finally, in order to have this information, as I said, in real time, we also found a way to integrate all this software in a portable, let's say, computational devices such as electronic field book. But nonetheless, let's start with instrumentation. We started, as I said, with commercial off-the-shelf spectrometers and quickly realized that none of the spectroscopic methods which we choose or spectrometers which we choose are comprehensive enough, allowing to detect all the types of different minerals and rocks that we actually can observe, let's say, on each of the Pangaea analog, planetary analog sites. Well, of course, we already looked for the minerals which are abundant on the Moon, Mars, and in other planetary bodies and meteorites. So we already knew that the type of instrumentation we selected, either it is vibrational spectroscopic methods or it is atomic spectroscopy methods. Each of them has its own benefits and drawbacks. But it was also became very quickly clear that if we combine, for example, the mineralogical composition with chemical composition, we significantly can increase accuracy. And that is actually became our main motivation behind developing future instrumentation, which can be used as, let's say, portable spectrometers, which can be used not only on the rovers, but also can be used by the astronauts on the field. And fortunately for us, ESA supported us, and actually ESA now initiated the development of these combined portable spectrometers. And this is the efforts which is done with the help of industrial consortium and experts in developing instrumentation. And these instruments are developed in order to be actually used by the crew on the field. So our involvement in this, we provide in additional calibration, we provide for this development also validation samples, and we also develop our software specifically to be used with these instruments when you have different types of spectroscopic methods in order to provide the real-time identification of minerals. Okay, and so, as I said, the part of this is a petrographic catalog. The catalog essentially contains all the necessary essential information in order to recognize minerals and rocks and the composition of these rocks on the field. The second part, spectroscopic database, is a compilation both from the open access archives, which are available, and some of the names of all of you know. But in order to complement these open access archives to the spectra of, let's say, less available minerals, we also did our own measurements. And currently, let's say for the Raman spectroscopy and reflectance spectroscopy, we have about 10,000 spectra for more or less 617 minerals that we have in our planetary analog database. And finally, we also developed our machine learning software. And the main focus on this, as I said, was data fusion. Data fusion is a term used when you combine the measurements from different types of analytical methods in order to provide a better classification. And the choice was obvious for us because we found that machine learning method allow, even though it's very computationally intensive, when we create a machine learning model, this model can actually do, when you have already this model, can provide very fast classification, really in near real-time classification, even in the portable devices, such as the electronic field book, which is currently the tablet. So far, to summarize all of this, we have already the software which allows to communicate with the spectrometers, collect all the data from this, allows to do the classification using our machine learning models, and not only providing information on the results of this classification, which is mostly would be not only the minerals and the composition of these minerals, but also provide information of significance of these discoveries, which is extremely important for a person in the field who doesn't have like minutes to understand what specific composition means. So to summarize, the current status of the project, we already have the partly working system, which is more or less consists of three important parts. The first one is a catalog, and currently, as I said, and it shows here, we have 600 something minerals. The most abundant minerals what we can detect on the Moon, Mars, and asteroids is a proxy of the minor bodies. 10,000 spectra for each of these spectroscopic methods, specifically molecular spectroscopy. And finally, you can see some statistics, what kind of, our data set consists. Finally, for the machine learning software, we have currently the machine learning models with different, let's say, systems, which allows to do supervised and semi-supervised classification. Both for the supervised classification and incremental learning, we can actually significantly adapt our machine learning to specific usage of the instrument. Everything is a modular, and we also had a chance in Pangea training to test real-time and real performance of our machine learning on the samples which are collected on the field. And we have statistics for the, specifically here, I showed just a combination of the map. And this is, in our view, is the most optimal usage in terms of trying to include information for all the possible minerals at the same time with high accuracy. And as I said, our tool altogether comes as a set. Therefore, we intend to provide not just only classification software. We would like to provide real-time decision support, not only classification of minerals, but also all the necessary information for the crew and science support rooms, so we can quickly make decisions. There are no weeks to analyze this when you're on the moon. And finally, we also testing this during the Pangea training, so we have real-time also experience of getting the comments from the people who are using the software, which is also very important. User experience and user advices is extremely important for us. Thank you for your attention. If you have any questions, you can actually look on all these references or just ask me any questions either at this conference or just send me an email. Thank you.
Thank you. Okay, thank you. Now, next one is Rognini that is connected. Mercury
Yes.
Lunar Exploration with Matisse tool.
Okay.
Are you ready?
Yes, yes, I am. I share screen.
You have 10 minutes. I will tell you 2 minutes before.
Yes, ok. Condividi schermo, ok. Sì. Ok. Just a moment, please. What's wrong?
We're not seeing your screen yet.
Yes, you have a problem. Just a moment. Things slow. Just a moment. The screen sharing is loading. Very, very slowly. Do you hear me?
Yes,
Okay.
we are still not seeing the.
Good. Sorry, I have a problem. I stop the sharing and I restart. Sharing. Che c'è? Oh, okay. Okay, let's restart. Okay.
There we go. It's coming up now.
Okay.
Yes, now it is working. Presentation.
Okay.
Here.
Do you see?
Yes. In the
Okay, sorry. Okay.
You have to start in the presentation mode.
Sì. Okay. My connection is very low.
Down there is the bottom presentation mode.
Okay.
The bottom it should be.
Ammazzo. Inizio. Okay. Okay. Sorry for the delay. Good afternoon. I am Edoardo Rognini. I work at the Italian Institute of Astrophysics and at the Space Science Data Center. And in this presentation, I want to talk to you about the lunar surface exploration with the Matisse tool. Un attimo, vorrei levare. Okay. Sorry. So, what is Matisse? Matisse is not Harry Matisse painter. Matisse is acronym. Multi-purpose advanced tool for instrument for the solar system exploration. And this is a tool for the analysis and the three-dimensional visualization of the data that come from the mission for the solar system exploration. Matisse is developed at the Space Science Data Center of the Italian Space Agency. And the SSDC works on acquirement and management, the processing and distribution of the data from spatial mission following the FAIR principle. As you probably know, FAIR is an acronym for findable, accessible, interoperable, and reusable. And the SDC is a result of collaboration between different research institutes as the INAF and the institutes. The work of the SDC spans several fields of astrophysics and aerospace science. The solar system exploration, obviously, for the part of Matisse, but also stellar astrophysics, cosmology, computation activation, Earth observation, the high energy astrophysics, and astroparticles and cosmic ray. The operative approach is that the developers and the users belong to the same community. So by using Matisse, what a user can do? By using Matisse, we can visualize the data directly from the tool. We can visualize three-dimensional models of small bodies. And a thermophysical model has been set in Matisse in order to calculate and predict the surface temperature for some ALS bodies as Ceres and Mercury. There is the possibility to get data based on geological units, that is not only by geographical coordinates as longitude and latitude. And the Martian radar data have been also added to Matisse thanks to the collaboration with the MARTIS and the GMAPS teams. The current version of Matisse is named Matisse 2, is completely written in Python 3. And with this version, we have the user can have the access to the VIR data of VEST and Ceres, the CRISM data via Planet Server, the MARTIS data that are publicly available, the Virtis Venus data via APN TAP, the data of Mercury MBS and AC, and then as the thermophysical modeling and the geological mapping. It's a pleasure to inform you that Matisse earned the place on the cover of Nature Astronomy Journal, thanks to our work on the Comet 67P by Tosi et al. 2019. This is a demonstration on how Matisse is powerful and efficient in management of the shapes of irregular bodies. In the right plots, you can see two examples, Vesta and the Moon. I'm going to talk about two particular tools that we are inserting in Matisse. The first one is thermophysical modeling. First of all, why is the thermophysical model is important? It's important because the knowledge of the local thermophysical properties as thermal inertia, thermal conductivity, emissivity, and so on. From this information, we can infer the composition and the physical structure of the surface. From this, we can determine the nature physical status of the soil. Particularly important are the diurnal cycles in surface temperature. That is the temperature as a function of time, local solar time, that is strongly dependent on the physical thermophysical properties of the surface. This is a reminder of the physical basis of a thermophysical model. We have to numerically solve the one-dimensional equation where we have the temperature T as a function of time T, depth X, with this surface condition that comes from the surface. The different physical inputs are reported in this legend. And the key thermophysical properties is the thermal inertia, defined by this equation, the square root of thermal conductivity times density times the specific heat. In this plot, we can see two example application of the thermophysical modeling and the graphical capability of Matisse. In the left plot, we have a comparison, example of comparison between observed and calculated temperature for a spot on Ceres. By comparison between observed and calculated temperature, we can retrieve the thermophysical properties, so the thermal inertia and from this thermal conductivity. And in the right picture, we have an example of calculated thermal map generated with Matisse in the case of the Occator craters on Ceres. Actually, the moon is not included in the thermophysical model, but we want to include the moon as soon as possible. Another important point is that in general, thermophysical modeling can also help in selecting landing sites in future in-situ mission, because as I said in a previous slide, by using thermophysical modeling, we can retrieve the physical status of the soil. We can say if a soil is made of fine dust or bedrock, for example. And this model has been also selected for the CLIVE research team as a part of the survey. And the second tool I want to show you is relative to the geological mapping. In this year, we have worked in order to improve the functionality of Matisse, incorporating geological maps of various celestial bodies in the solar system, including Mars, Mercury, etc. And now we are also focusing on the moon. We collaborate with the Plan Map GMAPS teams. And the left picture, we can see an example of a part of the methodology used. The geological map is loaded in the Geographic Information System software, the GIS. Then the polygon that represents the geological area is extracted and then is inserted in Matisse by using a Python code. In the right picture, we have the initial screen of Matisse tool, where the user can select the geological units of the planetary bodies. This is another example of selection of geological units in the case of Mars and Ceres. Yes. And now I want to show you a movie in order to explain how to use Matisse. Let's start. Okay, as you can see, the user can select the target, the mission, the instrument. We can select the geological units. The care is submitted, and the results are the images of the selected area. The result can be displayed by using several color scale. Okay, this is an example. And okay, the second part of the movie is similar to this. So I go to the conclusions and the future work. A key point is that thermophysical modeling and geological mapping are complementary. What does this mean? By using the geological mapping, we can select an area to be simulated with the thermophysical modeling, and vice versa. By using thermophysical modeling, we can determine a physical structure of a portion of the surface, and from this we can identify a particular geological unit. And what about the future work? The future work, we want to work on another area of the moon, Mercury, Mars. We want to add other data sets, cassettes, etc. We want to expand the possibility of searching for data based on the type of area you want to analyze, for example, craters, etc. We want to implement a new function for the surface analysis, and insert high solution, digital terrain model, digital elevation model, and the shape model. So with this, I have concluded my presentation, and thank you for your attention.
Thank you. I connected Eduardo Fornest for the questions. Now, Eric Malaret, Lunar Quick Map, new mission planning capabilities.
Hello, my name is Eric Malaret from Applied Coherent Technology. Very happy to be here to show you some of the new developments in Lunar Quick Map related to mission planning capabilities. Very upfront, I'm showing you some of the high-level capabilities and results in Quick Map, in case I run out of time. On the left-hand side, you see a 3D simulation star shape showing tracks of the sun, the moon over a particular period of time. And also you can see on the bottom here, like tracking cameras that wherever you are, they are pointing at entities that are very relevant to you, like the sun, the earth, the lander, and also nadir pointing cameras. On the right-hand side, what you actually see is a traverse being executed by an astronaut. Let's see, is it playing? For some reason, there. So basically, you can control the speed, how fast you speed this up in time, but normally it's a walking speed of an astronaut going through the traverse. Far away, you can see the actual starship is starting to lose contact to the starship if it continues on that path. And there's a lot of metadata information that is shown on the top. The rest of the presentation will elaborate on this, but at least you already have an intuition of what are the capabilities that are coming in this new mission planning tool. For those of you that are not familiar with QuickMap, this is a product that it has been in existence for over 10 years. We have been collaborating with Arizona State University and NASA, the LRO project. QuickMap has a lot of similarities to other data viewers, but has a lot of uniqueness that are very specific. The philosophy is that we want to have geophysical parameters in numeric data accessible. So you can put a dot and extract a profile. You can put a blob region and extract a data cube. You can inspect over any of the spatial profiles over the data. And it gives you a lot of capabilities for accessing the data, visualizing, doing sensor fusion. You know, the list is long, but the purpose of this presentation is not to go over what is QuickMap. But I need to highlight, last year we added a class that we call Terrain. And Terrain always provides you the best DEM that is publicly released and available. So no matter where you go on the moon, you will have the best resolution of data that has been publicly released. And that's very powerful because it gets updated automatically with every time ASU does, they do a update to PDS. Then there's another tool that is called QuickMap Terrain Shadows that allows to do synthetic lunar image modeling. So you can simulate shadows, even in the pole where some of the shadows can come from 100 kilometers away. And as a function of time, and this can be very precise computations, or it can be very interactive also. We were blessed to have over 700 unique users, depending on the metric is higher, per day. And I know that it's over 2 petabytes now of lunar data that is in the system. That number is all 1.5 petabytes. So With QuickMap, you can do rapid environmental assessment of lighting conditions with the new capabilities, and that's very important. I will try to move quickly away from what it was, but show you some of the new enhancements that we have been adding. There are enhancements that have been done to QuickMap, also that involves adding new data layers, adding capabilities to generate mosaics, basically next matching illumination conditions at some future time. And also, let me do this here. Okay, yeah, here you see on the right-hand side, you see an actual showing a solar eclipse actually happening, simulated in QTS 3D. What I like to concentrate a little bit of time is there are many new layers that we added this year. What I'm showing you is already available in the public QuickMap. There are a lot of new diviner data. There's a new group that is LROG-NAG A3 sites. That is basically as new data is published for over the candidate landing sites for Artemis 3, it starts showing up in that group. There's something very relevant that happened in this version of QuickMap that is now in 3D, when you go to the poles, it renders very nicely. It's polar optimized, and you can see data that is, you don't see a lot of gores going into the poles. It looks quite nice. Also, you can navigate with a gamepad controller. You can connect it to QuickMap, and it's like you're flying a drone over the surface of the planet in the poles. You also can load your own temporal geotiff cubes. On the right-hand side, we are basically illustrating this layer not matching illumination at some particular time. This is a very powerful new layer that was added. It's constructing a mosaic on the fly that is how the lighting conditions are going to be at that point in time in the future or in the past, using NAC images that match those illumination conditions. It's generated on the fly, and it's quite powerful. Let's see, next slide. Here is a comparison of the NAC machines illumination to actual simulated data coming from the QTS 2D, where it's purely simulated, and you can see they match quite well. Why that's relevant? Because when you don't have NAC images, now you can simulate the data. So you can try to use the best you have in observations, or you can switch to simulated data. There's a new capability in QTS 2D. We created a console mode. QTS 2D allows to generate high quality, highly precise illumination conditions, including shadows coming from far away, and including surface temperature, sunlit regions. But we have expanded the QTS 2D now to deal with when you have a large number of time intervals, maybe the whole calendar year or more, that you like to compute data. And we're calling these conditions and evaluation cubes. Short, we call them ice cubes. And they are really temporal geotiff files. But this is extremely powerful. When you are interested in going a candidate landing site or so, you can generate these ice cubes, and you can then interact with them as they provide you highly precise information of a illumination condition. One byproduct that it has there is hours of light ahead, which means that you put a pixel at a given time, and it tells you exactly how many hours of light you will have, for how much time you will have data. 2 minutes. This is a product where you see yellow basically is the actual hours of light ahead, that you at least have 6 days of light. That's an example. Let me switch here to QTS 3D. Now in QTS 3D, we can simulate the different conditions. We can generate traverses. We can generate a traverse, design a traverse, and visualize the traverse. Let me give you more insight into this. When you evaluate a traverse, you can also see here, this bar tells you when you have visibility to the sun along the traverse and to Earth. or to let the lander. This is very relevant because here you see you lost connect visibility to the lander in this region of the traverse. Or you can go to a particular point and say, at this point, show me over time, what is going to be my visibility. And these bars here give you the exact times that you're going to lose visibility to sun, earth, or lander also. There are many capabilities in the new version of QuickMap Terrain Shadows 3D. This is basically over Tycho doing flying a drone, but you can also have another mode that you can attach to the ground, and basically you are navigating the actual rover over the ground. This is great for if you're planning a rover or landing, you can use this to plan a mission. There are excellent views of this Tycho crater. I'm not going to let it go all the way. We also added a capability that gives you panoramic views. No matter the lat long and height, you can say, give me a 360 view, and it gives you that amazing view that you see here. And you see the tracks of the sun and also of Earth as a function over that period of time, at that time, over the time of interest. Concluding remarks. Well, we have new capabilities that allow users to develop a comprehensive intuition and understanding of the lunar environment via interactive sensor fusion, first-person view, flyovers, and ground perspectives. We have updated the QuickMap system. QTS 3D new capabilities are under password control. The IceCube data products can be generated on the request, and these are highly precise cartographic data cubes. We plan to continue adding Artemis relevant data. We refined the traverse simulator, incorporate a hub-key photometric model, support astronaut training with QuickMap and QTS 3D. And we are exploring creating a standalone version of QuickMap that can be for a particular region that doesn't require to have the internet connected to it. QuickMap, basically, you can run it on any device, including from your iPhones to any web browser. Presently, there's a lunar QuickMap that has been in existence for a long time, Mercury QuickMap that is being used also by Bepi Colombo. We are collaborating with Johns Hopkins Applied Physics Lab, and it has all the messenger data. Mars QuickMap, it has all the new data releases from CRISM, and they are all functional. We're getting close to release a version of Enceladus QuickMap, and we welcome your feedback and how to keep improving it for lunar applications. If you haven't used it, please use it. You will find it very simple to use. Okay. Thank you, Eddie. Thank you.
Please stay here for the question. I invite Igor to come here and Eduardo Wayne that should be still connected. Eduardo had to sign up. There are any questions for the speakers?
If you have any questions later, please look for me.
Okay, I have a question for Wayne. Looking at your chemistry map, which kind of data do you need for having the similar product for the moon?
So we can, currently we have various data models for Earth's rocks. So we have geochemistry, and then we have a lot of geochronology type things like uranium, lead, fission track thermochronology, argon, and things like that. But we can also create new models. So there may possibly be in the future a new type of data that needs to be collected on the moon, and the way that we've designed the system, we could actually incorporate that and then show it in a spatial way, if that's what's needed to be done.
Okay, thank you. Oh, there is one question here.
I'm very impressed by how you treat the data. I wish I had that when I had my own data. I have a question. Do you have is that online training or a tutorial to make use, for instance, of a quick map That's one question. Is there a standard training program we could apply, for instance, in our classes in the university? And second, is it only quick and dirty map, or can you generate product that you can use in scientific publication?
The output of QuickMap you can use in scientific publications is very precise. Some of the products are generated on the fly, but others are not. Are basically these are well-registered maps. I missed your first question.
Is there like a tutorial how to go into QuickMap and
There
for all
are
of us?
some basic information under the online help. It's on the left-hand side on the screen under a question mark. We think that it will be appropriate because the use keeps increasing to generate some videos in use cases, how to use QuickMap for this or other regions. But the tutorials that are there for QuickMap terrain shadows are very detailed, and they give you a lot of examples, for example. So it's something that we can always improve in the tutorials.
It's a self-taught, or do you also organize practical sessions with? Like I remember at LPSC, sometime in the past, we had some sessions where we could have a tutor and guiding us how to use those tools. So.
We like to get better. The basic idea, QuickMap should be as simple to use. I mean, it's almost intuitive. I like to give it to my nieces and to try things and let them see how they respond using it, because.
And then us.
Thank you. Any other question?
Thank you for the presentations. Probably I lost this part regarding the Pangea project. Do you intend to distribute the software component open source or free to use after the end of development?
Well, currently we are not allowed to share the code. The part which are already publicly available is a catalog. So both the graphic catalog and our reference spectra are open access, and they're available on data on Mendeley, for example. And we just updated actually that catalog at the beginning of the year.
And second part, do you intend to make some try to compare the data from the mineralogical recognition with some satellite data, just to have some, if it's possible to actually compare this type of data? Do you have any intention to make something like that?
Well, we are working on different scales. So just to be clear, we are trying to develop the tools which work really in the contact with minerals. So essentially, it's less than centimeter scale. And satellite data is definitely has to deal with other effects, as you know. Solar illumination is not a problem, for example, for us or shadows, because all our tools have their own internal illuminating sources. At the same time, I can now already say that some of our reference libraries, like reflectance libraries, are used for the, let's say, for the matching of, let's say, the clusters which have been found and with the real minerals. And Freya would present a poster tomorrow. She already used our reference library, for example, for this, using her own software, which is also machine learning based.
Thank you.
Thank you.
Okay, thank you again to the speakers. Okay. Thank you, Wayne and Eduardo. We close the session on the software.
So we have come to the final session of the day. Bear with us because it's an interesting session. I will first introduce Taizad from ESRIC for a talk about autonomy and operations for lunar rover science and prospective missions. Okay, presented by Matt Cross. Okay. So Matt, you are online and you can start. You can see your presentation.
We're not hearing your audio yet, though. Yeah, can you make sure the right microphone is selected? And if it is, quickly rejoining the meeting might help, but we can't hear you right now.
All right, can you hear me now?
Yes, we can hear you now. Thank you.
Perfect.
Just bring up your slides again.
All right, thank you very much. We had a quick change in presenter as my colleague Kezad had to go to an alternate meeting at this time. But yes, I will be presenting our talk on autonomy and operations for lunar rover science and prospecting missions. So at Mission Control, we develop software for Earth, Moon, and Mars. And our two core software products are Spacefarer, which focuses on the user operations for conducting mission operations, either terrestrial analog operations or for upcoming lunar rover operations, as well as our Spacefarer AI software product, which is intended to enable autonomy by deploying AI models for spaceflight hardware. Our Spacefarer software product has thousands of hours of analog use and is now supporting missions upcoming to the moon, as well as our Spacefarer AI software now has flight heritage on 2 flight deployments at this time. So one of the challenges for lunar surface science operations is really understanding the surface context, specifically for identifying hazards, being able to map and provide context for geologic and scientific targets of interest on the surface, as well as for doing instrument targeting. And so not only is are these challenges to science operations, but being able to improve upon these operations will then help drive and increase the amount of science return on any particular surface mission. So what we help to develop is autonomous perception capabilities for surface mobility and science operations. And so having this capability of autonomous perception really unlocks a number of capabilities such as obstacle prediction, understanding the mobility of the vehicle that is performing the science operations, planning out like mission traverses and being able to increase the amount of activities done per unit time, supporting automated instrument targeting, identifying how the resources of the surface asset is managed, as well as how the data is managed, including science data, and being able to prioritize high priority science data for downlinking. So autonomous perception is a key enabler in being able to improve and increase the amount of science return on surface missions. So one of the products that we have developed and demonstrated is our MoonNet capability. Now MoonNet was the first demonstration of deploying deep learning AI to deep space and lunar orbit. So it is an image segmentation model that is able to identify and segment out images captured by a lunar vehicle. And there's a number of interesting capabilities that are enabled by having this onboard capability on the rover to help improve with science-based operations. So one use case, an example use case would be automated targeting of instruments. So in the first step, the rover captures an image in front of its position, and then being able to segment out the different features within that scene. For example, rocks versus regolith versus craters, can then better enable autonomously targeting based on the type of feature that it sees. So for example, a crater might be of interest for identifying if cold trap potential, and may be used for auto targeting a thermal IR imager. Whereas a rock or a boulder might then have interest in characterizing the mineralogy of that feature, and could then automatically target some kind of multispectral imager. And also could provide automated targeting for a LIMS instrument. So having this ability to automatically segment out images within the scene can help improve and enable autonomous targeting to help increase the science return. Another potential example of this capability is downlink prioritization. So when the mobile platform or the rover has the ability to capture more images than can be downlinked by bandwidth constraints, a system can segment out and identify those features within all of the image sets, and then be able to identify and rank those features and prioritize them for downlink. So for example, if downlinking or identifying craters is a high priority, then those images with crater features or a greater number of crater features would be prioritized and then downlinked. And then so this would be useful for example, like identifying strategic decisions for prioritizing certain novel features and key science targeting. Another use case would be supporting operations for science teams by being able to pre-annotate images on the ground. So when the science team is on the ground is looking to conduct operations and prioritize what their next course of action would be, being able to pre-annotate features within a console to better communicate with their operations team members their intentions for which features they want to pursue and target. This is just an enabling feature that helps to improve the process of operations and increase or save time during that process. So one key demonstration of this MoonNet capability was recently demonstrated as part of our Lunar AI demo. We were a payload customer on board the recent iSpace Hakuto mission, and so our small form factor spaceflight computer was integrated onto the iSpace lander, which successfully launched and entered lunar orbit. There was a landing attempt, which unfortunately was not successful. However, we were able to demonstrate that our MoonNet payload was operational in lunar orbit. This was going to be demonstrated in part in collaboration with the Emirates lunar mission. So our MoonNet payload, which was hosted on the lander, would be performing its segmentation on images captured from the Rashid rover during its operations. So unfortunately, we weren't able to do that in-flight demonstration of that capability. However, it was still a significant success in demonstrating that it was functional in lunar orbit, and we do greatly acknowledge the support provided by the Canadian Space Agency for this capability demonstration. The way we envision this capability being deployed in this architecture would be the rover capturing images. Those images would have been classified on the lander, the data downlinked, and then having those segmented images available to the user would then help identify and improve the decision-making capability of science team users interested in furthering their science capabilities. So another capability that we are advancing and demonstrating is our Spacefarer operations software. And so this is what allows users to operate their mission. And so this has been developed out of lessons learned through thousands of hours of analog missions with science users contributing and defining the types of features that they want to use out of an operations software. And our most recent demonstration of using Spacefarer was at the ESRIC Space Resources Challenge. So Mission Control participated in the Space Resources Challenge. So we were one of the 13 participants that participated in the 2021 challenge in the Netherlands. We were then invited back as one of the 5 finalists in the 2022 challenge in ESRIC. This was an analog environment in which us as a team were able to use our Spacefarer product to operate our rover in an analog setting in which we had 5 in-person team members on site in Luxembourg, as well as 3 remote operators, all able to view and participate in the mission using this software tool. So our our integrated system was fully integrated with Spacefarer. We had 2 instrument partners providing a path to flight lunar instrument prototypes. And those were integrated onto our COX rover with standard GNC sensors. We had a LIBS prototype that was loaned by Impossible Sensing, as well as a LiDAR sensor prototype loaned from MTA. And so we integrated these into our system for conducting this lunar prospecting analog mission. And so it just shows the capabilities of being able to integrate in different instruments into the software platform for conducting lunar science and prospecting. Our approach was basically really focused on operational readiness and having our system available in our indoor lunar facility, integrated with all the hardware pieces, and as well as Spacefarer to enable remote participation and remote operations, really helped improve our operational readiness through an analog setting, which we believe is critical to successful lunar missions and lunar operations. We really do believe that high readiness is key to success. So just in quick summary, our belief is in Spacefarer and Spacefarer AI as tools for helping improve lunar science autonomy and lunar science operations. And so thank you very much.
Thank you, Matt. Very interesting. So the next talk for this session about instruments and tools for lunar exploration will be given by Cristina Luna. And will be on designing a modular multi-purpose rover for future lunar missions.
Thank you, Leonardo. My name is Cristina Luna. I'm a robotics project manager from DMB. And today I'm going to present you the European rover system, a new initiative by ESA. With this talk, designing a multi-purpose rover for future lunar missions. Okay, I'm doing my best, I promise. One, so I think maybe, if not with the, well, by hand. Thank you. Great. The talk goes as follows. I'm going to introduce the project and then go into the rover with the baseline, the locomotion concept, and also the onboard software and autonomy part, and the test campaign. I would really like to also talk about the thermal analysis and energy budget, but only 10-minute talk, so I will do my best. Okay. EMRS is a multi-mission project, which means that the rover needs to do many different things depending on the mission. In the beginning was targeted for 3 missions, now it's for 4 missions. The first ones are the Polar Explorer and the ISRU pilot plan. The Polar Explorer 1 is devoted to put the rover on the South Pole on the moon, and dedicated to extract some water ice volatiles, and also to develop some geophysical science there. And the South Pole, you know, there's a nice illumination conditions, also a good communication status, so it's perfect for lunar geological mission. Also, the ISRU plan is a complete different mission because the rover needs to carry almost 300 kilos of regolith, and to transport this regolith to the pilot plant, able to extract resources from them. The next missions are the Lunar Geological Exploration Mission and the HALO mission. The Lunar GEM is similar to the Polar Explorer in terms of the requirements, but it's targeted to 3 different scenarios on the near side of the moon. The HALO, many talks on this conference about the mission, is targeted to mount a complete astrophysical observatory on the far side of the moon. That means that the rover needs to be able to deploy antennas and to assemble the observatory. That means, of course, that the rover needs to carry a robotic arm, a robotic manipulator. In this case, we are designing the GMB Lunar 1. As you can see on the right picture, it's targeted also to put objects on the moon and to assemble them, planetary assembly rover. Okay. The project team is a consortium led by GMB in Spain, with the collaboration of ABS from Spain, also with HDR from Greece, OHB and DLR from Germany, and GMB from UK also. Moving on to the rover, EMRS is a multi-mission rover that should be launched on the Argonaut. So it's one of the first Argonaut passengers. That means that we have a really constrained requirements of terms of space, because Argonaut has limited space for that. So it left on these dimensions, rover that on a stop position has a shape of almost 2 meters, on a deploy position 2.5 meters. You can see here also that we have this stop and deployed position, has different footprints. That's because we have designed a rover focusing on modularity. And in this case, the modularity for us is there's 3 different bays we have for payload. The central bay on yellow is devoted to the main payloads of the rover, the wheel controller, the thermal controller, and the common payloads for every mission. The side modules on green are devoted for other kind of payloads that need direct access to the surface. For example, a drill, or a spectrometer, the GPR, or any other scientific tool like that. On top, we have this blue bay that is suitable for a mast or a robotic arm that we saw in the sample. This configuration, this design with the 3 different bays, allow us to configure the rover in many different ways. For example, you have here the ISRU configuration with the shovel, the drum, and the robotic container, and also the Polar Explorer one configuration with the drills or the spectrometers on the side. That's the thing for a rover for multi-purpose. It needs to be modular in this case. So the locomotion baseline is a 4-wheel rover with 4 independent suspension and steering. The wheels are wheels from configurable stiffness, or it can deflect depending on the interest. This leads in different locomotion modes that you can see on these pictures. The point turn that allows the rover to do a complete turn on the same spot. The crab turn is rotating with the parallel wheels, and also single and double Ackermann, and of course, apart the steering mode. We have this suspension that you can see is a spring with motors, because we are using a mixed suspension concept. It's a passive and active one that allow us to go on passive where you are traversing a flat surface and you don't need to put so much strength on the suspension, and also allow us to do this walking mode, like moving one wheel and another, it is legs, for example, to be able to overcome some obstacles, or also to increase the ground clearance or to put the rover directly to the surface. Regarding the steering, maybe you have noticed that the steering motors are on the side of the wheel and not on top. Usually the rovers used to have the steering motors on top of the wheel. But in this case, after real effort on the design, we thought that it was a better idea to put the steering motors on the side because it allows us to the space available on the Argonaut and also to perform in a better way the operations of the rover. In terms of software and autonomy, this is the part of the wheel control and also the camera's control. We have selected for the breadboard and OBC based on the Siemens Korea KR260, which has a space grade sister, so it's really easy to develop something for Earth that can be directly migrated to a space software. These things include all the winds controller, steering, thermal control, and every common payload controllers. But for having this multi-mission concept, we need a really high level of autonomy, E4 level for European standards. So we decided to reuse the software developed from TISRU and AIDE Ergo projects, the Peraspera ones, which means that we are having this level of autonomy with different models of perception or manipulation, multi-agent capabilities in case of, for example, the ISRU plan that we could have many rovers in the same place, and also to be able to communicate with the control station to the moon base other control parts. Regarding this perception component, we developed also this AI-powered software suite that enable us to perform this astronaut-robot collaboration for complex robot-robot on astronaut-robot scenarios. Because also in the fourth missions, it is not planned yet to have astronauts around. We really thought that in the meantime, there will be the rovers working with the astronauts alone. So we made a data set on, as you can see, on GMB spot on the left, high seas at Hawaii on the center, and also the ESA's planetary lab on the right, to be able to detect the astronaut and rover interaction, and also the astronaut panels and other parts of the moon-based interaction. That's an example of it interaction. You can see is the astronauts and the robot on a maintenance mode. That also allows us to perform a safe navigation, where we call it social navigation. It's the rover moving from, around the surface without putting in risk the astronauts and also the other robots' status. In terms of the test campaign, we developed this breadboard. You can see with the aluminum profiles. On the picture, we didn't test it with the side modules and top module because there was a locomotion test. But you can see it's the double Ackermann right now. And going deeper, these are pictures for the test campaign. We wanted to get some kind of goals in terms of traversing, excavation, and other locomotion and software tests. You can see on the top right picture that we were able to traverse up to 25 degrees of the slope. The crab turn, point turn, and double Ackermann test, of course. On the bottom left corner, you have this uneven terrain traverse. As you see, the wheel is deflecting, we're passing the rock. Also, the obstacle overcome, of course. And one of the most important things that we test at the LR with the Regolith simulant, that we indeed are able to excavate on the moon with this kind of concept. So let me finish with a question. Why to design one rover per mission when we can just design one to rule them all? Thank you.
So thank you, Christina. The next talk will be from Negar Fer about the flexible logistics and exploration, Flex rover and robotic arm with modular payload capability.
Thank you. Thank you, everybody, and thank you for staying this late, especially the fact that we've gone over and you're still awake. That's great. So I'm excited to tell you more about our flexible logistics and exploration rover at Astrolab, which we call Flex in short. So Astrolab is a startup based in Hawthorne, California, which employs about 20 to 30 engineers with a lot of experience working on lunar and Martian rovers on almost every single arm that was flown on the Martian rovers, as well as numerous missions at JPL, SpaceX, etc. I'm very excited to be working with this team that basically has a vision of a multiplanetary future. And I imagine the fact that you're sitting here in this audience today tells me that you believe in the same thing. Otherwise, you wouldn't be attending a lunar symposium. So we think we're today at this crazy inflection point, thanks to all of the investments that are going into reusable, fully reusable, let me say, rockets, rovers, landers, and all the equipment that's being invested in today. And in fact, there's been about $1 billion of investment in the past decade, which is a threefold increase compared to what it was a decade ago. So there's been a lot of traction, which basically allows us to have unprecedented access thanks to these reusable vehicles, like what you see right here, which is the Starship vehicle. I'm sure you're all familiar with it. And what we believe is the next evolution of what's needed in order to enable last mile logistics is a rover. Similar to the previous presentation you saw, we believe in that vision as well. And the Flex rover that we're designing, unlike most rovers you see today, it has actually a lot of payload capacity. It can carry 1.5 tons of payload on the surface of the moon, and it can go at 15 kilometers per hour top speed. It's semi-autonomous, and it will stay on the surface of the moon for a period of up to 10 years. And I'll tell you more about it soon. Oh, what happened to my presentation? Oh, maybe we can skip the video. It's not playing. Well, I was excited to share a video with you, but every time I press on it, it closes the presentation. Yeah, let's skip to the next slide. This 6. You can go to slide 6. Thank you. Okay, so the Flex rover is designed to be very versatile, meaning that it's modular. It can carry, 2 fully suited astronauts, or it can carry, multiple tons of cargo, or both. And the reason why we've designed it this way is in order to enable not only, NASA human exploration missions, but also all the other infrastructure that we're going to need to build on the moon. And the next slide. Thank you for bearing with me. I'm not sure why my presentation keeps closing. Sorry, 7, forward play. The video is that one. Well, I had a really cool video to show you. Thanks to the video not working, I can share the YouTube link with you later to show you about all the cool what's going on? Thank you. I appreciate that. So, you know, today it's an amazing time to be living. You know, we thanks to rockets such as Starship that are going to be landing on the moon circa 2025, 2026. Don't ask me the exact date of these missions. That's still not public knowledge. We are basically enabling a feature similar to what you see with cargo ships, where you know they come into a port with a lot of shipping containers, and then such as trucks and trains to get things to where they need to be. We see a similar feature, and that's why you're designing large rovers that will take cargo out of the Starship garage, they call it, down an elevator and to destinations where habitats and other things will want to be established. We'll be able to take multiple tons of cargo, not just what fits on our rover, but go back to the Starship lander and pick up packages and deliver them where they need to be, so that we have a very nice end-to-end system. Our rover is designed to enable a lot of different kind of missions in this fashion. And it's modular in the sense that your payload doesn't have to be assigned. We also have other type of payload accommodations that are in like 12-year form factors. So don't worry if you're not like 2-ton payload and you want to do a mission, you can still enable that. But also for future missions, it's going to be 2 tons to do that as well. As you see, we have 2 solar panels on the side that deploy. We have a 6-gun robotic arm connected to the rover that can deploy those payloads out of central 12-view compartments or other types of compartments that we have on board. And the really revolutionary thing that it can do is establish all the types of infrastructure around the moon that critical solar arrays and power systems are needed to enable more energy-intensive type of applications on the moon. The rover has capabilities to enable ISRU, all types of extraction applications, as well as transporting humans. You know, fully suited astronauts, we believe, are easier to be transported in the standing configuration thanks to all the equipment that they have. So we'll pick them up on Starship lander and other landers that enable human landing systems and transport them to eventual habitats and other things that they'll want to do. Hopefully enable all the missions that you guys are working on as well, be it manned or autonomous. You can see the wheel, the chassis, all the support is designed to be able to withstand all the different slopes and environments. It can do crowd walks and all of the types of different configuration with the wheels. And we eventually anticipate to have not just one lander, but multiple landers on the moon that can enable creating habitats and things of that nature to build larger scale infrastructure for the needs of astronauts and others. That configuration rover right there. And we are not, we're kind of lander agnostic. Yes, we are going to go on the first Starship mission, but we can also go pick up cargo from other landers, such as Blue Origin and other heavy lift vehicles. And we hope to standardize the payload that come off and be able to go pick them up and transport them where eventually we need to. You know, here's showing an application where we're enabling resource extraction and manipulation, and we can take these samples back to other sample return missions. And yeah, enable the full lunar economy. So we see transport as a key, transportation and mobility as a thing that really needs to be solved to enable the future. 1 minute. Okay, so I'll go through these quickly. I already talked about our robotic operations. The robotic arms that we've developed can also operate in 1G, so we can use them here on Earth as well. They can carry 25-kilogram payloads and do all different types of extraction missions. We're going on the first Starship mission to the moon, and we've contracted somewhere in the middle of 2026 through 2028, carrying tons of payloads. We've signed customers already for this mission, but we do have additional capacity if you're interested in flying with us. We are doing quarterly field testing. So if you're looking to do analog testing, this is part of our culture. We do testing all the time, and we take our customers with us on these test campaigns. And this is just showing you our development plan. Can I go through it or? Okay, so let's see if I can do this in 20 seconds. So this is showing you the whole development plan. It starts with transportation and data logistics. And then we're going to move into enabling energy collection and storage, which we think is the next big piece, and distribution of that. And with the higher levels of energy, we can enable heavy energy use applications, such as extraction of resources on the surface of the moon, which will then lend itself to establishment of a permanent human presence. So I wanted to thank you, and sorry for all the technical snags today. My email is there if you have any questions about Astrolab or want to see some more of the videos I was unable to show. I'm happy to share that with you, and I appreciate your time today.
Thank you. So the next and last talk for today is by Claudio Pernechele about the PanCam, a bifocal panoramic camera for lunar exploration. Claudio.
Thank you, Leonardo. So we are very hungry now. I go faster. And so I will speak about a bifocal panoramic camera, which is a new camera we designed in INAF. It is a panoramic lenses with the capability to have two focal lengths simultaneously. And so we found 4 applications for lunar science, and so I will describe briefly you. The core of the PanCam is the bifocal panoramic lens, which is a panoramic lens that look at 360 degrees around the azimuth and 100 degrees in the zenithal angle, 60 above and 40 below the lens horizon, and simultaneously by means of a frontal optics. Yeah, you see the mouse. By means of frontal optics, we can have also a second field of view with a much longer focal length. And if we place a folding mirror here, we can see at the panoramic field and with a short focal length, and another image with a longer focal length, so with higher resolution. The second image is formed, the high resolution image is formed in the center of the donut-shaped panoramic lens. And so the PanCam is completed by using a image sensor, a bidimensional image sensor, and eventually by some FPGA, I don't know, possibly, or depend by the application. All the ancillary instrument like the image sensor, the FPGA, SCB is available on the market, Scots, and so is a technological level of 9. And so the bottleneck of the PanCam is just our lens, bifocal lens. And so actually it is at 4 in TRL, and we plan to have a TRL 6 in 2 years now. So that's the four applications we found. We are studying now. All 4 are funded. Funded for a feasibility study, and one is regard the panoramic surface monitoring that this morning Francesca told about. One for the human exploration, the plume cam for monitoring the lander of exhaust plumes from a lander, and the Daedalus cam for exploring the lunar caves and lava tubes. So the first application is the EMM PanCam. Francesca instead Francesca tomorrow, this morning, will describe it in detail. So we are planning to design, we are designing the thermomechanical mechanical mount of the lens, and we are planning also we built in our laboratory a very big chessboard to calibrate the image distortion just in one shot. That's the lens. That's the 4 meter take chessboard. That's the image seen by the lens, and so we can calibrate the distortion. The second application is the Omnicam, which is a motorized pancam led by Leonardo. Okay, that we test it just in Lanzarote Island during a Pangea training campaign for the ESA astronaut. And so we have, you see here the panoramic view of 360-degree in azimuth and 100-degree in zenithal angle, and the enlargement of the astronauts that is here in the panoramic field. So it is motorized because the geologist from the control room may move the camera to look around some interesting scientific target. The third application, which just 1 week ago entered in the ESA reserve pool of science activity for the moon. It was selected. Our idea is to monitor the exhaust plumes from a lander just in the landing phase. We also, just for fun, we mount a lens on our drone, and you see here the contextual image, and that's what's the lens, the panoramic lenses look from inside, from below the drone. So we have to study the effect. The last application is the Daedalus cam, which is use 4 pan cams. And so it is able to look at the entire volume in stereoscopic mode. That means that, for example, I don't know, the 0.1 or 0.2 is every point, every point in the environment, in the surrounding is seen, but by at least 2 cameras. And so we can reconstruct by stereoscopic the distance. And simultaneously, we can use 4 colored channels for scientific purpose to be used for the geologist. We realized also a mock-up. You can see we can see it tomorrow in the poster section, just in the table, exposition table of the Leonardo, the space click design. And so very fastly, that's the last slide. We have here a series of references if you wanted to go in depth in this application. It missed a last paper in the Daedalus cam by Emanuele Simeoni that we written 2 months ago for the International Conference of Lunar Caves held in the Lanzarote Island. So that's all from my side.
Thank you, Claudio. So we are very late. We have just time for one single question. Should there be any? And all the authors can come up here to answer the question. So I don't see any raised hand. So I will ask you for one very flash question, which is for the Lunar Explorer, Polar Explorer. What is the degree of autonomy of the rover if you are planning to have, or you are envisaging to have an autonomous mission, let's say an autonomously driven mission?
The current degree of autonomy is E4, which means that the rover can autonomously do everything. I mean, you can, of course, have the human in the loop to operate the rover, having lower levels of autonomy, it's possible, but the rover itself is able to select the samples that it needs to collect, and to perform these activities autonomously.
Thank you. So with this, I think we can close the schedule of today. Thanks for attending. And tomorrow morning, we will be back here at 8:30. Just a note on the social dinner of today. We will gather at Ristorante Zairo in Prato della Valle, but all the information is on the website if you. That's all. Thank you. See you tomorrow.